Hello everyone and welcome to the PCD for Codeforces Round 1034, Div 3. Am I audible? Can someone confirm in the chat? Also, how was the round, guys? Was it easy, hard? What's your opinion? Round 1034, Div 3. Okay. Yeah. So let's just get started now. We'll cover all the problems all the way from A to G, right? And we'll discuss each one by one, spending the appropriate time on each of them. Seems harder than Div 2, really. To be honest, I thought it was easier, on the easier side of Div 3, but okay. Anyways, we'll go through all the problems regardless. There was quite a bit of number theory and construction type of problems, so I guess maybe that's why it was a bit harder. Not sure. Anyways, problem A. Also, before starting, of course, I would like to tell you that TLE self-paced courses are out right now. Yeah, so just go to the website TLEeliminators.com, check it out if you haven't already. We have courses across 4 different levels depending on where you are on your CP journey right now. And there's a sale which is going to end very soon. And yeah, definitely do check it out if you haven't. We have more than 40 hours of practice problems, say 40 hours of recorded lectures, more than 100 practice problems, hints and video solutions for each problem, as well as non-stop doubt support available. So anytime you're stuck at a question, you can just make a new doubt. You'll be assigned a mentor, and then you can connect one-on-one with that mentor to clear your doubts and stuff. So if you want such an ordered approach to uh, CP, then definitely go ahead and check it out. Satvik, what do you mean by copy pasted E? Um, I would definitely discourage such behavior, right? That's against Codeforces rules. So please refrain from such behavior, right? Um, Most probably, if you copy pasted anyways during rollbacks, they're gonna flag you, right? Yeah. Thanks, Vijay. I think I'm not sure if this was my first or second div 3 where I solved all the problems, but yeah. Anyways, let's get into it. Problem A, blackboard game. Initially, the integers from 0 to n minus 1 are written on a blackboard. Okay. In one round, Alice chooses an integer a and erases it. Then Bob chooses an integer b such that a plus b equals 3 mod 4 and then erases it. Rounds take place in succession until a player is unable to make a move. The first player who's unable to make a move loses. Determine who wins with optimal play. Okay. So simple game theory question. I guess most people would have gotten A. Maybe there are some people who didn't get A, so I'll just explain how it works. Game theory and a little bit of number theory, right? These are the topics which this question covers. So if you want to know where in TLE these topics are covered, they'll be covered in level 1, because in math for CP it will have basic number theory as well as basic game theory ideas. So that's where this question is from, right? That level. Okay. So let's quickly see what observations we're getting for this problem and see how to solve it. Okay. So let's just take the first example. Okay. Let's take one example where Alice wins and one example where Bob wins. So in the first example, example 1, there are numbers. So the n equals 2, right? So that means the numbers 0 and 1 are written down. Okay. The numbers 0 and 1 are written down. Now let's say Alice chooses the number 0. Okay. If Alice chooses the number 0, then Bob needs to choose a number. See, Alice choose A equals 0. Now Bob needs to choose a number B such that A plus B mod 4, right? So remainder with 4 equals 3, right? Now the thing is, what kind of number can he choose? Well, since A is 0, he needs to choose some number such that B mod 4 equals 3, right? So he has to choose some number which is leaving remainder 3 with 4. So it can be 3, it can be 7, it can be like so on, all numbers which leave remainder 3 with 4, right? So it can be 11 and so on, right? But as you can see in the array, there is no 3, there is no 7, there is no 11, etc. because the array ends off at 1 itself, right? So that's why Bob is unable to find such an element. So therefore Bob loses because he cannot make any move, right? So that's why the answer over here is Alice, because Alice wins in this case. Alice wins, right? Now let us have a look at the second example. Yeah. Okay. Now in this example, we can see that Bob wins. So we're seeing both types of examples. Okay. Now here you see 0, 1, 2, 3. Okay. Now what happens? Let's say, let's just randomly pick an element and say Alice chooses this. So let's say Alice chooses this element A equals 1. Now Bob, so that Bob does not get eliminated, Bob needs to pick some element, which is B equals um, something like this, right? He needs to choose some element B such that this condition is satisfied. 1 plus B mod 4 equals 3. All right. And what possible value can give 1 plus B mod 4 equals 3? Well, in this array, we can see that 2 is giving that value, right? Because 2 plus 1 is 3 and 2 plus 1 mod 4 is 3, right? So 2 gives that value. If there were some elements like 6, then 6 would also give it, because 6 plus 1 is 7, mod 4 will be 3, right? So if there was 6 in the array or there's 2 in the array, those values will satisfy, right? So that's why we can say that Bob will take 2, right? Bob will take B equals 2, and then he will satisfy this condition. Now let's say Alice takes 3. Okay, next Alice takes 3. So this one Alice takes next. Now you can see that 3 plus 0, which is the remaining element, that is the only element left. Mod 4 is also 3, right? So that's why Bob can take this. Now Alice is left with no moves because all the elements are taken. Alice is left with no moves. Therefore, Bob will win, right? Bob will win. Now, I think by this much, you should have already gotten the pattern. Like I saw the first two test cases and I got the pattern. And with practice, you'll be able to see the pattern quickly, right? A big part of CP, like, see, there are two parts of CP, right? One is to build your logic, and one is to build your pattern matching. And while logic building is our ultimate goal, the helpful part about pattern matching is it helps you solve problems fast. Okay. But yeah, now let's go through the full logic of what exactly is happening here. Um, so yeah, so what we can see is when we have a number, if A was 0 mod 4, right, then B should be 3 mod 4. Okay. If A was this, then B should be 3 mod 4. Okay. That's what we can draw this conclusion, right? Because if we pair 0 and 3 mod 4, then only we can have overall 3 mod 4. Now, if A was 1 mod 4, then B should be 2 mod 4, right? This is basic modular arithmetic, I would say, right? Because we want them to sum to 3 mod 4. Therefore, if A is 1 mod 4, then B must have been 2 mod 4, right? Now again, if A was 2 mod 4, then B should have been 3 mod 4. Sorry, then B should have been 1 mod 4, right? And if A was 3 mod 4, then B should be 0 mod 4, right? So basically, no matter what Alice, if we want it in such a way, such that we want Bob to win, okay? We want to know when Bob will win. We want to know. So this is our main idea. So this is observation, right? This is an observation. And now we're going to get the idea from this observation, right? This is our observation, which we saw the two test cases and we observed this. Now this is going to be our idea. We want that the number of elements, okay, number of elements such that it is equal to 2 mod 4. So what will I call that? I'll just call it, like, we can write equal to symbol like this, and we can say 2 mod 4. Okay, so the number of elements equal to 0 mod 4. Okay, number of elements, or we can say congruent, right? In number 3, we say congruent. So the number of elements congruent to 0 mod 4, let's call that A of 0. Okay, number of elements congruent to 0 mod 4, that should be equal to number of elements congruent to 1 mod 4, equal to number of elements congruent to 2 mod 4, equal to number of elements congruent to 3 mod 4. That means the number of elements which leave remainder 0 should be equal to the number of elements which leave remainder 1, and so on, right? That's basically what we want in 0 to n minus 1. Okay. And this is true for which n? This is true for which n, right? And if you write the arithmetic progression, right, 0, 1, 2, 3, if you write that, obviously, as you can see, it will cycle through. If you write it with modulo 4, right, it's going to cycle through all the values like this, right? So it will be 0 mod 4, 1 mod 4, 2 mod 4, 3 mod 4, 0 mod 4, 1 mod 4, 2 mod 4. So that means every time this point happens, right, every time this point happens, it will happen at 4, it will happen at 8, it will happen at 12, and so on. Then there is an equal number of all three congruent classes, right? Then there is an equal number of A0, A1, A2, and A3. So therefore, we can say that Bob wins. Bob wins if and only if n is divisible by 4, right? Bob wins if n is divisible by 4. N is divisible by 4. Otherwise, Alice wins. Okay, that's all. Very short and sweet conclusion. The code is hardly 2 lines, and for each test case, we can answer in order of 1. Okay, this is the time complexity, right? Is the code even needed for this? I don't think the code is needed for this, but I'll show it to you anyways. Yeah, so simple code. If n mod 4 is 0, then Bob, otherwise Alice. Okay, any doubts in the question, or should we move on to the next question? Rating of D. Maybe 1000, 1200, something like that. That's what D felt like. Maybe 1000, 1200 actually. Maybe 1000, not sure. I brute force in n square. It's all right. Yeah, okay, next question. Let's go to question B. I forgot what B was, but okay. Right. Okay. Okay. You're given an array of integers, A1 to AN, and the tournament is held with the n players. Player I has strength of A of I. Okay, so there's some n players. Each player has some strength. Till more than k players remain, choose two players at random. Then the chosen player with the lower strength is eliminated. Okay, so we're going to do this until k players are remaining. We choose two players and at random, and then eliminate this lower strength one. If the chosen players have the same strength, then one will be eliminated at random. Okay, so if the strength is same, we just eliminate one at random. Given integers j and k, determine if there is any way for player j to be one of the last k remaining players. Okay, so this is also somewhat straightforward if you look at the examples, right? A lot of the questions seem to be easy if you look at the examples. N goes up to 10 power 5, so we are expecting big O of n solutions, right? Let's get right to it. Problem B, right? Problem B. Okay, so let's take an example. Okay, so we do a game where there are 5 players. We want the second player to survive till the end, and we will repeat the matches until 3 players are alive. Okay, and the strengths of the players are 3, 2, 4, 4, 1. Okay, so these are the strengths, or these are the values of A. Okay, so we want to do this until 3 players are alive, and we want this guy to stay alive in the end. Okay, so what we can do is maybe we can have a battle between these two, right? Since their strengths are equal, one will get eliminated, right? So let's just pick one and eliminate him. Now we can have a battle between these two, right? Since 4 is greater than 1, that means 1 will get eliminated. So now our array looks like 3, 2, and 1, right? Our array looks like 3, 2, and 1. And what happened? Um, what happened? Basically, yeah, our element 2, which had to survive, it has survived, right? Survived till the end, right? Till k players are remaining, right? So if you think of this like a game, right, the logic comes very instantly, I would say, right? We need them to survive until k players are remaining, right? So that's why since he has survived, the answer is yes, right? So yes. Now what do we need to do? Um, right. So immediately on just seeing this example, right? First idea we can get, or idea we can get is um, try to not even let our player participate in any battles, right? If he does not participate in our battles, then he won't lose, right? So it's like being overprotective parents, like do not let him participate in any battles itself. So then he'll try, like, if he does not participate, he can't lose, right? So we'll just keep him in the array, right? Try to let the jth player not participate in any battles itself, okay? Not participate in any battles, okay? Then what happens? Like, it's like we have these bunch of elements, right? And we take the jth one, right? We take the jth one and we just keep him separately, right? And then the battle happens between these guys, right? The remaining guys, they battle until exactly k elements are remaining, right? And the thing is, we need to determine if there's any way, right? Not some, like, not at some, like, we don't need to determine if he can fail. We just need to know if is there any chance he can win, right? So just because we need to know is there any chance he can win, well, one thing which can happen is he never even participated in any battle, so he could never be removed, right? So for n greater than two, for n greater than sorry, not for n greater than two, for k greater than two, k greater than or equal to two, we can always do this, right? We can separate j and let the other n minus one elements fight it out, and that way, for k greater than two, the answer will always be yes. Okay. I hope that makes sense, because if we need only two people remaining, right? So one, we can keep this guy separately, and then the others can fight out until one remains from them, right? And then we have only two people remaining, which is this guy and the one who beat all the others, right? Similarly, for k equals 3, 4, 5, we can just keep our chosen one separate. Okay. Next, what? What if k equals 1? Okay, what if k equals 1? What if k equals 1? Well, if k equals 1, then there can be only one person alive, right? In the end, there can only be one person alive. And since the strongest will beat any weaker one, right? The strongest will beat any weaker one. It's going to be basically like a death battle, right? It's a death battle amongst them. So then if k equals 1, then j is only going to survive if he is the strongest, right? J will only survive if he is the strongest. Jth guy is only going to survive if he is the strongest one, right? If he is strongest, right? So basically, we already solved the problem. If k greater than or equal to, answer is yes. Otherwise, if k is equal to 1, we need to know if he's the strongest, right? If there are multiple strongest, then still he has a chance, since it's random between them, right? So that's why we can write our final answer. If k greater than or equal to 2, or um, a of j equals max element, right? Equals the max element in A, you could say, right? Answer is yes. Otherwise, the answer is no. And that's the full algorithm, right? In straightforward big O of n, we can solve this, right? The code is also very simple. I don't think much to see here. We take in njk, we take in our vector A for each element. If k is, yeah, so I wrote it in the opposite way, but yeah, if k is 1 and he is not the max element, then it's no. Otherwise, it's yes. So it's the same thing. I just wrote it in like opposite way. But yeah, that's all, right? So that's the code. Time complexity is big O of n. Understandable? Yeah. This was pretty easy, I think. B was almost 800 level question. Okay, so you said if J equals min and the only min. But think, Aditya Sharma, if K was 1, right? If K was 1, that means only one guy can live till the end. Am I correct or not? That's what I said. If K equals 1, only one guy can survive. So it's going to be a death battle, right? So even if he's not the minimum and he's not the maximum, he's in the middle. He's going to die to the strongest, right? Only the strongest will get to survive for K equals 1. Okay. All right, so let's go on. Let's go to the next question. J is zero indexed, yes. The person who asked J is zero indexed, no, it is zero indexed. Should we go to the next question, guys? Yeah. I think from C, the problems start getting interesting. A and B were, I think, pretty simple. Okay. So let's read the problem C. You're given an array A of distinct integers. In one operation, you can choose some non-empty prefix of A and replace it with the minimum value, or choose some non-empty suffix of A and replace it with maximum value. Now you may choose entire array A. Okay, we can choose note that we can choose the entire array A if we wanted. Okay. Now for each element A, output if there exists some sequence to transform the whole array to A of I. So to make it contain only one element, which is A of I, output your answer is a binary string of length n, where the ith character is 1, if it is possible, otherwise 0. Okay. So just read the question. N goes up to 10 power 5, so we expect, I guess we will expect the big O of n or big O of n log n solution, right? So let us see an example. So let's just directly see the example without writing it, right? We can see it here itself. So our operation is basically choose a prefix and make it equal to the minimum of the prefix. So if we choose this prefix, we can make it equal to 1, right? Because minimum of this prefix 1 and 3 is 1. So we can make this thing equal to 1, right? Similarly, if we chose the whole thing as a prefix, right? It said we can choose the whole array. So if we choose the whole array as the prefix, then we can set it to 1. The whole array can be set to only one element, which is 1, right? And that's why it's possible to set the whole array to 1. That's why we can write 1 over here, right? Now, these are impossible cases. Let's see how the 7 case is possible. Okay, let's see how the 7 case is possible. It's the maximum, right? So simply we choose the whole array as suffix, right? And in suffix, it becomes the maximum value, right? So we choose the whole array with 7 as the suffix. So then the whole array becomes one element, which is 7, right? So that's why this one is also possible. So obviously minimum of array and maximum of array will always be possible, right? Now, how is 2 possible? Let us see in this test case, how is 2 possible? Okay, because that is the only other element which looks interesting, right? Problem C, example 1, right? And we have the elements 6, there are 6 elements, and they go 1, 3, 5, 4, 7, and 2. Okay, yeah. So now, how can we make 2? How can we make only one element remaining, and that element should be 2? Okay. Now, clearly, if we do a suffix like this, right? Clearly, if we do a suffix like this, what happens? What happens is that this whole thing, right? This whole thing will become 7. So the 2 will just get wiped off, right? It will become 1, 3, 7. The 2 will just get wiped off. So we cannot use any suffix operations right now, right? We can't use suffix operations right now for 2, right? So what other method do we have? Okay, what other method do we have? Well, here's an idea. Let's choose 1, okay? And let's take this much as the prefix, right? Take this much as the prefix and make it the minimum value possible, right? Make it the minimum value possible, right? So now what happens? Um, Now what happens? Since this is the minimum value possible, our array becomes 1 and 2, right? Basically, we eliminated this 7, this large 7 which was in our way. We eliminated it. Now we can use 2 as the suffix, and we can convert our array to only 2, and this will be our final answer, right? So that's why 2 is possible, okay? Why is 3 not possible? Let us see. These 3 elements are not possible, right? Let us try to see why 3 is not possible, okay? And let us see why that happens. So the reason is if we do any operation like this, right? If we do any prefix operation on it, then this will become 1. Correct? This will become 1. And if we do any suffix operation on it, right? If we do any suffix operation on it, then what happens? This will become 7, right? It will become like 1 and 7. So either side we do any operation, right? Either side we do any operation, nothing is going to help us, right? If we do the operation from this side, or if we do the operation from this side, nothing is going to help us because this will always become either 1 or 7, right? And it can't stay 3, right? So what is the intuition behind this, right? So I think today's problems were a lot about seeing the examples, making observations, making a guess, and then proving that guess. Okay. So I can't just logically, like, it's very nice to do deductive reasoning sometimes, but here it's hard to do deductive reasoning. It's more like you make the observation, then you prove the observation afterwards. So first the observation comes, then the proof, right? And here's the observation which you can make after seeing some test cases, right? Basically, or you know what? Before making this observation, let us see another example, okay? That then the observation will be more obvious. Let us see one more example to make it very clear what's going on, okay? And my example is going to be 1, 2, 3, 4. I'll make my own example, and 5, and let's say 2, 2, 2, and 5, 4, 3, 2, 1. Okay? Let's say this is my example. Or maybe like something like this. 5, 4, 3, 2, 1, 2, 2, 2, 2, 5, 4, 3, 2, 1. This is going to be my example, and this example will make the whole problem very clear. Okay? So now if we want to make all elements equal to 5, okay, or let's say this was 6 over here, just to make it more nice of an example. Okay, now we want to make all the elements equal to 6. Right? So currently, right, is there any step of operations we can use to make all the elements equal to 6? Well, since this is just the max, so obviously we can do suffix max, right? So leave this element. Let's try the element 4. Okay. So we know that since this is just the maximum, right? So we can just take the whole thing as a suffix and do maximum. So we can leave this, right? So this is 1. Now what about 4? Is there any step of operations to make all the elements equal to 4? And the answer is yes. How will we do that? Well, here we can do a minimum, right? So it's only 4, right? And then what we can do is we can take this from 3 to 4 and make it 5, right? So what happened to array? It becomes 4 and 5, right? So we took maximum on the right side and we're taking minimum on the left side. Then the whole thing again will do prefix minimum and it becomes only 4, right? So this idea works. This idea works because there's nothing smaller than me to the left of me. Okay. That's what is our key observation. There's nothing smaller than to the left of me. Then I can make it equal to this using the minimum operation. Similarly here, I can make this equal to 3. Then I can make this equal to 5. Now for 3 and 5, I can take minimum and get 3. That's why this is also possible. Okay. If you observe, this is also possible, right? Now, what about 2? 2 is also possible. Why is 2 possible? Because I can take this whole thing, make it 2, right? I can take this whole thing, make it 2, take this whole thing, make it 5. Then I get 2 and 5 as my array. I take prefix max of the whole thing, I get 2, right? So then this is also possible. Similarly, 1 will be possible, right? What about 2? This won't be possible. And why won't it be possible? Because this won't be possible because um basically at this 2, there's this 1 which is smaller than me, right? Because there's an element which is smaller than me to my left, right? It is kind of blocking my way. So if I take minimum of this, it becomes 1, right? It does not become 2, right? That's why this one is not possible, this one is not possible, this one is not possible. Okay. Now let's do the whole thing in reverse. Okay. What if we wanted it to be 1? Well, we see that 1 is already the minimum of the array, so it will be possible, right? What if we wanted it to become equal to 2? Okay, and we can make it equal to 2 also, and I'll show you how. We take max of this, right? Max of this becomes 2. Now we take min of this. Min of this becomes 1, right? Now we have 1 and 2, right? Now we have 1 and 2, and we take max of 1 and 2, like suffix max becomes 2, right? That's why this 2 is possible, right? Similarly, this 3 is possible, 4 is possible, and 5 will be possible, right? So this is our idea. And after this, the observation should become pretty clear, right? For each element, from left to right, okay? For each element from left to right, if there is a number, if there is number smaller than me to my left, smaller than, actually just for each element, not from left to right, that doesn't really matter, right? For each element, if there is a number smaller than me to the left, right, then it's not possible with the first technique, right? The first technique is take like this minimum, take like this maximum, and then take the minimum of the whole thing. So that technique is not possible, right? So not possible with that way. And then the second technique is we take maximum this way, minimum this way, then we take the max of the whole thing, right? So then for that, the second technique is basically if there is larger to the right of me, if there is number larger to the right of me, so not possible with technique one, right? We can call this two different techniques of solving. Technique one. And if there is number larger than me to the right, than me to the right, not possible with technique two. Technique two, right? So if it's possible with either technique, it should be possible, right? It should be possible with either technique, it should be possible. What is the first technique? The first technique is technique one, possible if this is the smallest number to occur so far. If this is smallest number to occur so far from left to right. Okay, from left to right. Okay, and technique two, what is technique two? So it's basically the same things which I did for the examples, right? I took the left side min, right side max, and then I took min of both. This is technique one. Technique two is left side min, right side max, and max of the whole thing, right? So this is possible if largest number to occur so far backwards. Okay, largest number to occur so far from right to left. Okay, okay. I hope this is understandable. And what does this mean? Can you see here one is the smallest, right? And after this, we can't use technique one on any of them, right? Similarly, 7 is the largest. So after this, we can't use technique 2 in any of them. So the answer is only 1 and 1. Okay. Now here, if we use this one, we can see that 13 is the smallest till now. So we can use technique 1 here, right? Then 10 is the smallest till now in these two. So we can use technique 1 over here. Now we can't use technique 1. And here 20 is the largest of the whole array. So we can use technique 2 for 20. But for 12, we can't use technique 2 or technique 1. So the answer is 0, right? Similarly, over here, we can use technique 2. 7 and 2 also we can use technique 2. We can't use anything here since 7 is larger. Here also 7 is larger. Here also 7 is larger, right? And again, here we can use technique 1. But for 3, 5, and 4, 1 is smaller than it. So we can't use technique 1 for them. So for these, the answer will be 0. Does that make sense, guys? No, not only min-max elements will be 1. It's only that basically if the current number is the smallest so far from left to right, then it will be 1. Or if the current number is largest so far from right to left, it will be 1. Okay. So if it satisfies either of the two conditions, it will be 1. Fine. Now, one more last thing we need to see a special case. Okay. Let's say our array was something like this. 3, 4, 2, 5, 1, 6, 3, 4, 2. Okay. And we have another 2 here. Okay. Let's just say we have this. Fine. Now, if we use technique 1, which ones become possible? This one becomes possible since it's the smallest so far, right? It's the smallest so far. Now 4 is not the smallest so far since 3 is smaller. So 4 is a 0 so far, right? 2 is not the smallest so far, right? So, sorry, 2 is the smallest so far. So 1. 5 is not the smallest so far, 0. 1 is the smallest so far, 1, right? Now all of these will become 0 by technique 1, right? All of these will become 0 by technique 1, right? Now we will try to use technique 2. So we use technique 1 so far. Now we'll use technique 2, okay? 2 is the largest so far, right? It is the largest from the right side, right? So that's why this will become 1, right? Now 4 is also largest from the right, yeah? So this will also become 1. Now 3 is not the largest in this suffix. Why is it not largest in the suffix? Because you can see that 4 is larger than it, right? So it is not the largest in its suffix. So this will remain 0 itself, right? Now again, 6 is larger than the suffix, largest in its suffix. So what will happen? 6 will become 1, right? Now all these numbers are smaller than 6, so we don't need to check technique 2 on them, right? So we are done. But we are not yet done, okay? We are not yet done because all the question asked was if final array can be made equal to A of I, can be made equal to A of I. It does not mean we need to start with this element itself and then make the array A of I, right? Because using operations including this element, we cannot make it A of I, right? If we just try to use technique 1 on 3 and 4, right, it will become 3. Similarly, if we use technique 2 on 4 to 2, it will become 6, right? So neither technique will work for this element. But here a 4 is possible, right? A different 4 is possible. A different 4 is possible. And because a different 4 is possible, that means this will also be possible, right? We can make the whole array 4. So then this will also become 1. That's because simply a different 4 was possible. Okay. What about 5? Is there any other 5 which is possible? And you can say that no, there is no other 5 which is possible. So that won't change. 2, is there any other 2 which is possible? And yeah, here it is. So this will be 1. 3, is there any other 3 which is possible? Here, right? So this will also be 1, right? So this is going to be a final answer for this example. Okay. And I hope this explains what I mean by technique 1 and technique 2, as well as that thing about making sure that if it is possible somewhere, then that possibleness propagates throughout the whole thing. Okay. So what do we write as our final algorithm? Okay, now we'll write the final solution. Final solution. So to make sure that we know whether an element is possible or not, we'll use the map data structure. You can also use unordered map, but I'm not sure, you might get hacked with unordered map, right? You know, hacking, in hacking, they sometimes blow up unordered map. So that's why we'll use the map data structure. It is log n, but okay, all operations are log n, right? It uses red black tree, so there'll be an equivalent in Python. There'll be equivalent in Java as well. So we'll use the map data structure, and map of each element will go to 0 or 1. Okay, so 0 or 1 means whether it's possible or not. Okay, and what we will do here, we'll say it can even be a map from int to bool, whether the element is possible or not. And then first we'll try technique 1. So we'll try technique 1. We go for I from 0 to n, right? From beginning. If x, or if a of I, if a of I is minimum in 0 till I, right? Then we can set that map of a of I is true, right? So this element is possible. Similarly, try technique 2. Okay. Try technique 2. And we can say for I from, in reverse order now, from I from n minus 1 to 0, right? Here it should be n minus 1, by the way. And we can write here, if a of I is max in I to n minus 1, right? If it is the maximum in the suffix, then technique 2 will work. And we can write, we can set this to true. So map of a of I equals 1. Okay. Now we can simply go through all elements in A. For each element x in A, we can output the value of map of A. Okay. That's it. Let it be int itself. That makes more sense. Okay. So we tried technique one, technique two. If it is working in any of them, we set it to 1. Then for each element, we check if it worked or not, and we print that as our output. And this is our final solution. What's the time complexity? The time complexity is big O of n log n. Okay. Big O of n log n. If you use unordered map or if you use arrays, it will become big O of n. So definitely you can try arrays or you can try hashing. But if your hashing is not good enough, it might get hacked. So that's why I just use normal map. Okay. So big O of n with hashing. Keep that in mind. Let us see the code. So I have a vector. I take in my elements. I define my map. Then I set my minimum to the maximum possible integer max, right? Infinity. If the current element is smaller than the minimum, I update the minimum and I set it to 1. I set this element to 1. Similarly, if the current element, so similarly, I do reverse, but for maximum, max is negative infinity. If the current element is greater than the suffix maximum, this is the new suffix maximum, and the possibility becomes 1. Finally, for each element, I print the output. Okay. I hope that explanation was clear. Yeah, you can use prefix min and suffix max. That's exactly the same thing I've done. I just did not make an array, right? I did not make any array for that. I just use this value stores my prefix min and this value stores my suffix min. So it does save memory. Can't we just take any positive size? I did not understand your question, Gurika. All elements are distinct. No, all elements are, wait, all elements were distinct or what? Oh, all elements are distinct. Okay. So I think I overcomplicated the problem here. If all elements are distinct, then we don't even need this map, right? I did not read the part that all elements are distinct. Sorry about that. Very sorry. Since all elements are distinct, no map is required. No map is required. Sorry about that, guys. Just change the code. Like you don't need the whole map thing. You can just directly set the current element to 1 or 0, right? So you can save. You can just make a array of answers, which is 0, right? And you can just set like answer of I is 1, right? Something like this you can do, right? You don't need the map. Then for each element in your answer, you can just print it. And then this should also give the same element answer. And this will be O of n itself, right? If all elements are distinct. Yeah. So it does the same thing. I did not notice all elements were distinct. That's why I added one extra step to the logic, which is to use the map, right? But it does not change the problem that much, I think, right? But yeah, it does make the time complexity big O of n. Anyways, let's move on to problem D, or are there any doubts? Things should be quicker. We're being a bit slow. Yeah. I think it's clear now. Yeah, it's the same thing I've done, Vridul, except if you make a whole prefix. Yeah, okay, no doubts. All right, let's go to problem D. I'll just quickly drink some water and then come back. Alice and Bob are given a binary string S of length n. Alice wins if she transforms all characters of S to zeros. If Alice is unable to win in a finite number of moves, then Bob wins. Okay, and what are their operations? On Alice's turn, she can choose any subsequence and set all the characters in subsequence to 0. On Bob's turn, he may choose any substring and set all the characters in that substring to 1. Okay. If Alice wins if all the elements become 0 at any point during the game, including in between Alice and Bob's turns. Okay, so if any point Alice can make the whole array equal to 0, Alice will win. Determine who wins with optimal play. Okay. So before getting into the question, before getting into the question, I want to tell you that this is a like constructive problem, right? So in constructive problems or ad hoc problems slash game theory, these types of problems, what we do is it's hard to logically deduce the answer. Like it is obviously possible to logically deduce the answer if you're very smart or something, but often you make guesses, and then once you make the guess, right, you see a lot of examples, you make the guess. Once you make the guess, then you try to prove the guess, right? So that's the approach I will also follow while explaining, right? I'll show you some examples. Based on those examples, I'll make a guess, and then based on the guess, I'll prove it or explain why that is true, and then show you why it works, right? So that's how it works. And how do you train the skill of making good guesses or having stronger intuition? You practice a lot of problems, right? That's how you get better at that, how you get better at constructive problems, right? Okay, so let's take an example. First, understand the question, then try to solve it for certain cases. So we can see that in 5 and 2, Bob always wins. And what is the elements? Okay, so now Alice can choose any subsequence, right? Alice can choose subsequence. By the way, before we start, n goes up to 10 power 5, so we need obviously O of an answer, right? At most. So Alice can choose any subsequence of size 2, right? And make it all to zeros. Bob can choose a subarray of size 2 and make it all 1, right? That's the operation they both have. And Alice goes first, right? Okay, and Bob goes first, right? So, sorry, Alice goes first. So let's say Alice takes these two and makes them 0, right? Now the array has not become all zeros. So now it's Bob's turn, right? Now what will Bob do? Let's say Bob just decides, okay, I'll undo what Alice did. Okay. And he'll just undo what Alice did and he'll put ones back here. Right. So that move helped us do nothing at all. Right? That move helps us do nothing at all. What if Alice said, I will undo these two? Okay, like I'll make these two 0. Sorry. So she can choose a subsequence and she can make it 0, right? So she'll choose this and this element and make them both 0, right? Now Bob needs to choose a substring and make it ones, right? It's not all zeros yet. So Bob can play. He needs to choose a substring and make it all ones. So let's say he chooses this substring. Okay. He chooses this substring and decides to make it all ones. Fine. Now what? He puts a 1 over here. Right? Okay. Now what happens? So still the game is going on. Alice can again choose any two and make them 0. So let's say Alice chooses this and makes them 0. Okay. Now what will Bob do? He'll simply undo that. Right? He can choose any substring and make it 0. Alice can choose subsequence. Bob can choose substring. So he'll undo this operation. Okay. What will Alice try next? Alice will, okay, let me remove these two. Now what will Bob do? What Bob does is he can choose these two and make them both ones. Right? So he can choose these two and make them both ones, since that's a substring and he made it once. Right? Now again, no matter what Alice chooses, can you see? Bob is always able to restore it, right? So if Alice makes these 0 again, Bob will just undo it. If Alice makes these two 0, then what will happen? Bob will just make like this, right? Bob will just make it like this. He'll change these two and make them ones. So he'll do this. Okay. Now Bob can, like, this is with optimal play. Okay. There's a way where Bob can make a mistake. Okay. And I'll show you how. If these are ones, and let's say Alice chooses 0 and 0. Okay. Now if Bob chooses this substring, right? If he chooses this substring of 1 and 0, then this becomes the array, right? Now Alice can choose these two elements, make them 0, and win the game, right? So Bob must be very careful. He should never do something like this, right? Bob should always choose two elements all over here and make them into ones so that he can keep playing the game forever and nothing will become all zeros, right? So then he will be able to keep playing the game forever and it'll never become all zeros. And that's why Bob wins, because he can keep playing this game forever and it will not become zeros, Bob wins. Okay, and this is our first example. Now let's see another example in which Alice wins. Okay, example 2, where Alice will win. And it is 7, 4. And the elements are 1, 0, 1, 1, 0, 1, 1. Okay, so this is our second example, right? And here we know that Alice will somehow win. Okay, and how is that possible? Let's see. One idea I can have is, so because I can't spend time doing each and every case, I'll just show you the idea itself. So what Alice should do optimally is choose this, right? Choose this, and she can choose 4 elements total in her subsequence, right? So then she will choose the last one as this one. Now what happens to the array? Only one element is remaining as 1, right? Only one element is remaining as 1. And what is that element? It becomes 0, 0, 0, 1, 0, 0, 0. Okay. Now the interesting thing is, no matter what Bob chooses, right? No matter what Bob chooses, he's going to lose in the next turn itself. Okay. So let's say Bob chose this subarray and made them all ones, right? If Bob chose this subarray and made them all ones, what happens? We get 1, 1, 1, 1, 0, 0, 0, right? And then simply Alice can choose these and make it all zeros, and Alice wins, right? Now what else can Bob try to choose? Let's say Bob chooses this. Now again, Alice will just make them all zeros and win. Similarly, Bob chooses this. Alice will make them all zeros and win. Bob chooses this. Alice will make them all zeros and win the game, right? And what we see is that no matter what subarray Bob is choosing, Alice can just always make it all zeros. Okay. So now here we'll make our key observation. Key observation. When it is Alice's turn, when it is Alice's turn, right? Bob needs to ensure there are k plus 1 elements equal to 1. Okay. Bob needs to ensure that there are k plus 1 elements which are equal to 1. Otherwise, Bob will lose directly in the next step itself. Why? Because Alice can just choose some subsequence of size k or less, right? She can choose any subsequence of size k and make it all zeros. So I think this is a easier observation itself. Like if we had 7 and 4 in the previous example, and this was our array, right? Then Alice can simply choose these and make it all 0, right? Even if it was something like 0, 0, 1, 1, right? Exactly k elements are 1. She can just choose these and make it 0, right? So this is our first observation. I hope it makes sense, right? So after his turn, Bob always needs to ensure that k plus 1 elements are equal to 1. Okay? So this is what Bob needs to ensure after his turn. Okay. So let us try the extreme case. Okay? Try the extreme cases. Extreme cases. Which extreme case are we talking about? Where exactly k plus 1 are 1. Okay? Where exactly k plus 1 elements are equal to 1. And let us see if Bob can survive this situation. Okay, let us see if Bob can survive this situation. So let's say we have the same example 7 and 4. Okay, so exactly k plus 1 elements are equal to 1. So let's say k is 4 and k plus 1 is 5. So we can see the 5 elements are equal to 1. Okay, now we can show that no matter which k plus 1 equal elements are equal to 1 here, Bob is still going to lose. And why is that? Well, what we can see is Alice will do the same thing she did last time. Okay. She will turn this to 0. She will turn this to 0, turn this to 0, turn this to 0. And it becomes this array of last time. Okay. Because what Alice did was the number of ones decreased by how much? The number of one decreased by an amount equal to, we can say minus equal to, right? Did the decrement operator by k. Okay. The number of ones decreased by k. Now what Bob is doing Bob needs to somehow restore all those k, right? If Bob does not restore those k, there will be less than k plus 1 elements in Alice's turn, and Alice will win immediately, right? So Bob needs to somehow restore k elements. Bob needs to restore exactly k elements somehow. Okay, he needs to restore exactly k elements somehow, and that he needs to do ASAP. Okay, he needs to do this ASAP in this turn itself. But it's not possible because what is happening is this one, right? It's overlapping with all the subarrays which Bob can choose, right? Bob is not able to find any empty subarray. It's overlapping with all the subarrays which Bob can choose, right? But what if n was equal to 8? Okay, what if n was equal to 8, k was equal to 4 itself, and we had a similar situation, right? And we had a similar situation, n equal to 8, k equals to 4, right? We got a similar situation like this. Now what the thing is, no matter which one is on, Bob will always find a way to restore k ones. Like he can turn all this to 1, and again we're back to k plus 1 ones, right? And then again, let's say instead of this one, Alice decided to turn this one on. Okay. Then again, Bob can just choose this, turn them all to ones, and we are back to k plus 1 ones. Okay. So basically, what is happening is if n is large enough, okay, if n is large enough that Bob is always able to restore, Bob is always able to restore, like he's able to undo Alice's move in such a way, restore the array to k plus 1 elements, right? That means he turned k elements to 1. He turned k elements to 1, right? Then Bob will win, right? Then Bob will win. And if Alice makes sure that he's not able to restore all of the k plus 1 elements, right? If he's not able to, if he is not able to, Alice will win. Then Alice will win. And yeah, so this you get by seeing some observations. Is the key idea for the problem, this idea, right? What does this look like? So how much big n is large enough? And if you observe, n large enough means n should be at least 2 times k. Okay, n should be at least 2 times k. And why do I say this? Because observe, in that also, as soon as it became 8, which is 4 times 2, it was possible, but when it was 7, it was not possible. And the reason is, if it is less than 2 times k, if n is less than 2k, okay, then what we can do is we can always choose the middle element. Okay, Alice can always make that the middle element is on, all the other elements are off. Okay, so Alice will turn every element off except the middle element, right? Alice will want to turn every element off except the middle element, and she'll force Bob into this situation, right? We can see, you can observe that she can always force Bob into a situation such that middle element is on and all the other elements are off, and then Bob will not be able to choose anything, right? If Bob chooses like this, he will not be able to get enough, right? So let's say here the example n is equal to 1, 2, 3, 4, 5, k equals to 3. Now 5 is less than 2 times 3, right? So if Bob chooses this, he won't be able to restore k plus 1 elements. Similarly, Bob will not be able to choose anything that way, right? Similarly, if k was equal to 4, then definitely 5 is less than 2 times 4, right? So Bob will only be able to restore this, right? He will not be able to restore k plus 1 once, right? Which he needs to do for Alice to not win, right? So that's the simple observation we need to make, that for Bob to win, two conditions must be true. So it's very constructive, this question. For Bob to win, condition 1, they should be greater than equal to k plus 1 elements in the start, right? K plus 1 elements in the start. K plus 1 elements equal to 1, right? Equal to 1 in the start. Second, n should be greater than or equal to 2k. And this will ensure that Alice cannot force a situation where the middle element is the only one which is 1. And then, like how will Alice force such a situation? She'll just turn the elements on the left and right off, right? Until Bob becomes the only middle element, and then what she'll do is then Bob will not be able to, will not be able to pick a satisfactory subarray, so Bob will lose. So for Bob to win, these two conditions must hold true, else Alice will win. Okay, and that's all for this problem. If you try the other test cases also, you'll see that these two conditions work perfectly, right? And let me just quickly open the pseudocode for this. All right, so we take in n and k, we take in the string. For all the elements which are 1, we increment number of 1. This is like a counter for 1. Right? So here I wrote the condition in reverse, but it's the same condition. If the number of on elements are less than equal to k, or n is less than 2 times k, then Alice wins. Otherwise, Bob will win. It's the same condition here. And the time complexity is big O of n, right? And actually, it's just big O of n to read the input. The whole logic itself can be done in big O of 1 if you know the number of ones in the string, right? So did you guys understand? I didn't understand why the number of ones must be less than or equal to k. See, if this is possible, it's OR condition, okay? It's OR condition. If this is there, then in the first step itself, Alice will make everything 0, right? If the number of ones are less than k, let's say k was 3 and k was 3 or k was 4, then she'll just make all of them 0 in the first step itself and win, right? So that's why that first condition is there. And the second condition is if n is less than 2 times k or not. Because if let's say if everything was 1, okay, even if everything was 1 and n equals what, how much is n? 1, 2, 3, 4, 5, 6, right? N equals 6. Let's say k equals 4. Now 4 times 2 is 8, right? And 6 is less than that. So what Alice can do is she will always find a way to make Bob lose. And how is that? She'll make the middle element 1 and then the rest she will make zeros, right? So she'll make this 0 and she'll make this 0. Okay. Now what can Bob do? He can choose either this subarray, or he can choose this subarray, or he can choose this, but it will never restore k plus 1 once, right? We notice that we need at least k plus 1 once before Alice's turn. Otherwise, Bob is going to lose immediately. And let's say he chose this subarray, okay? Then he made this 1, 1. Now in the next turn itself, Alice is going to make it all zeros and she's going to win, right? So that's all. These two conditions are required for the whole problem to be solved. All right. So moving on to problem E after this. If there are any doubts, just ask. I'll try to re-explain, but it's a constructive problem. So yeah, what is the raise? Is it always the case that the 1 is in the middle of the array? Yeah, usually it does not need to be exactly middle. If n is very small, then it can be somewhere in the side also, it's fine. But for the worst case, exactly if n equals 2 times k minus 1, in that she has to make it go to the middle and then she has to do it. How do we get penalty? Okay, so I'll tell you how penalty goes, okay? I think each wrong submission is extra 20 points of penalty, okay? Each wrong submission is extra 20 points of penalty. And the remaining part of your penalty is the sum of the times you solved, okay? So for me, the penalty will be 2, because I solved the first question in 2 minutes. So it'll be 2 plus 10, right? 2 plus 10 plus 18 plus 20 plus 38 plus, so this will be 62 minutes, right? Plus 62 plus 78. And this is 2 minutes, 2 hours, 3 minutes. So that'll be plus 123. And then I had 2 wrong answers. So plus 20 plus 20. And that whole element, that whole value will be 361. Okay. So that's how penalty comes. Can you tell how Bob will win if n by 2 equals k? I'll show that. Okay. How do you come up with this observation? Well, I can say by trying examples and practice. That's mostly it. If you want exactly n by 2, I showed you that case already. N equals 8, k equals 4, and n equals 8. I think I'd shown that, right? Just assume that, let's say exactly k minus 1 are on, right? Let's say 5 are on over here. 1, 1, 1, 1, 1, 0, 0, 0. And that's 8 elements, right? So 5 are on, k plus 1 are on, at least k plus 1 are on, right? And these 5 elements are on. And Alice will make any four of them equal to 0. So let's say Alice made this 0, this 0, this 0, and this 0. Okay. Then obviously Bob can just restore it, right? What if Alice made this 0, this 0, this 0, and this 0, right? So what if this happened? Now what will Bob do? Well, Bob will just pick this subarray and make it all ones. Okay. He'll just choose any adjacent subarray and make it all ones. That's what Bob is going to do in this situation. Okay. Uh, the eraser is glitching, but okay. And he'll make this all ones. Now you can see Alice kind of pushed him to the middle, right? Now what if Alice makes this 0, and like she only keeps the middle element on? Okay. So I said that that was a good strategy for Alice, right? To make the middle element forcefully on, right? So I get 0, 0, 0. Now what will Alice do? Now what will Bob do? Well, Bob can simply choose this, right? And he can restore it to k plus 1 elements again, right? And if he keeps doing this, it will be like a cat and mouse chase between Alice and Bob, and it will go on till infinity, right? Again, let's say Alice decides to erase these. Bob will just restore these, right? Alice decides to erase this one and these, right? Now Bob will restore from this side, right? So as soon as n equals 2 times k, Bob has one full side to restore. Either left or right, he'll be able to restore a full k block next to this one, right? So he'll ensure that k plus 1 ones are present. That's why this logic works, right? How long do we need to practice to trust these intuitions? To be honest, see, if you're in the end of the contest, just make a guess and submit, right? Because at that point, it will not hurt your penalty, all right? How long you need to practice? See, once you're pupil specialist, I think many pupil specialists solve this question. So definitely you'll be able to get it, right? Once you're a specialist, definitely I think you should be able to get it most of the time. Constructive problems are like that. They use some clever thinking, right? So that only comes with practice after some time. Okay. Should we go to problem E now? We'll just start it in a minute. To be honest, I found E harder. I'm not sure how there are so many solves. So maybe there was a simpler solution than mine. I found E slightly harder. Like the number of solves on E surprised me, I can say. I definitely do not think there'll be this many solves on E. So maybe my approach is more complicated than required. As you can see, I got a wrong answer on E as well. Yeah. Maybe there's a more simple approach than mine. But anyway, let's get into the problem. Okay. So we all know what MEX is. If you don't know what X is, it's the smallest number not present in an array. Okay. We are given an array A of size n. For all k from 0 to n, count the number of possible values of MEX after removing exactly k values from A. Okay. Communicated E in a very simple way. Well, I guess there might be some simple solution. Not sure. At least my way, I think, comes from fairly logical way. Like even if the code is longer, it's logical. So let's go ahead and explain my approach. Right? N goes up to 10 power 5 as usual. So big O of n log n solution. Okay. So we need to count the number of possible values of MEX. Okay. So because the question is a bit confusing, let's just take the first example, solve it. Okay. 1, 0, 0, 1, 2. And like for k equals 0, right? We can remove no elements, right? Remove no elements. So obviously there'll be only one possible MEX, and that is the MEX of the whole array, correct? There is no choice here. So for k equals 0, the answer is always 1. What about k equals 1? Okay. Now we can remove one element. Okay. And what are the possible choices we have? So obviously MEX of the original array, MEX of whole array is 3, right? Since that much, 3 is the smallest element not present, right? So MEX of the whole array is 3. Okay. Now, um, right. Now, what if we can remove one element? Okay. So either we can make it 0, like the order of the elements does not matter, right? So for now, I'll just pretend that it's in sorted order, since that makes it easy for me to visualize it, right? I think that makes it easy. The order of the elements does not matter clearly to the problem. So let's say I remove the first element, right? What happens? I get 0, 1, 1, 2. The MEX remains 3. Okay. What if I remove one of the ones? Okay, then I get 0, 0, 1, 2. The MEX remains 3. What if I remove this one, the last two, right? Then I get 0, 0, 1, 1. No 2, right? I remove the 2. Now the MEX is 2. Okay, can you see? MEX was 3, 3, and now it's 2. Right? And so the total number of possible MEX, that is 2. Because either it can be 3 or it can be 2. So for k equals 1, the answer is 2. What about k equals 2? Here we can remove 2 elements. Okay. Now for k equals 2, let me quickly erase and see what all possible arrays we are getting, right? And only write the important ones. Repeated ones I will not write, okay? So either we remove the 2, okay? Either we remove the 2 and we remove one of these elements. So we can get something like 0, 0, 1. Here the MEX will be 2. Otherwise, we can remove, let's say, both the zeros, and we have 1, 1, 2. Here the MEX will be 0. Or we have 0, 0, 2. Here the MEX will be 1. Or we keep, like, say, all or one of each, right? And in this case, the MEX will be 3, right? Does that make sense? So there's 4 possible MEXs, right? 4 possible MEX in the end. Obviously, we can't have MEX higher than this because, like, if you remove elements, then the MEX can only become less, right? If the MEX of the whole array is 3, then the possible MEX will only be 0, 1, 2, 3 if you remove any elements. So yeah, it has already reached the maximum number of possible MEX, which is 4, right? So this you should keep in mind. If the MEX of the whole array is 3, if you remove any elements, then the MEX will remain 3 or it will decrease. MEX cannot increase if you just keep removing elements. Okay? That's the first thing you should just note in your mind, like small note to be in the back of your mind as we solve this problem. Okay, so the number of ways becomes 4 because we can have 2, we can have 0, we can have 1, and we can have 3. Okay? Now what? Now we have only 2 elements remaining. Okay, now in the next step, when we set k equals 3, we can have only 2 elements remaining, right? And now actually, when there is only 2 elements remaining, right? A very interesting thing happens, right? A very interesting thing happens is that um, we can find that, one possible answer is 0, 1. One possible answer is, let's say, 0, 2, 1, 2, right? The others where it's 0, 0 and all, we don't need to care because that will just repeat the answer. Okay. And this gives us a MEX of 2. This gives us a MEX of 1. This gives us an MEX of 0, right? And then there are 3 ways. Now k equals 4. And then for this, there will be 2 ways because now there's only one element remaining, right? Now there's only one element remaining, and the element can be 1, it can be 2, or it can be 0. In each case, here the MX is 0, here the MX is 0, here the MX is 1. Two possible values, 2. Now k equals 5. k equals 5. Okay, what happens to k equals 5? Now the whole array is empty, right? The whole array is empty. The max will be 0. Max of empty array is 0. And there's only one possible, so 1. Okay, so you can see it kind of increased a little bit, and then it started decreasing, right? It started decreasing. And in fact, if you go see the examples, right? Leave this example, everything is 1 over here. But in all the examples, it's like 3 to 1, 5, 4, 3 to 1, 5, 4, 3 to 1, 4, 3 to 1. And interestingly, it's not just like that. They didn't choose the examples like that. It actually kind of happens. Yeah, I'm doing CP since 6 years, but then like I did a little bit when I was in 9th and 10th and onwards, but that was not much. Like uh I didn't even cross pupil until like for a long time. I was just doing for fun, right? When I came to college, then only I kind of got into it. Anyways, so yeah, one observation we can make, okay, is from the backwards case. Okay, let's see this from backwards. Okay, now we're going to start getting into the solution. So from now we're going to get into the solution ideas. If you want to get familiar with more examples, then do it yourself after the video, right? After the video, just go to the more examples. You might come up with the solutions yourself. So let's get into the solution ideas now. Consider k equals 5. Okay, consider k equals 5, right? Or k equals n. Consider k equals n. Okay, what happens at k equals n? The array will be empty, so the MEX will always be equal to 0. So there's always one possible answer. Okay, so that's why the last value will always be 1. Okay, that's why there's always a 1 at the end. Now consider k equals n minus 1. Okay, so that means only one element is remaining. Only one element remaining, right? Only one element is remaining. And in this case, the last value will always be 2. Like if the MEX was at least one of the original array, then the last value will be 2, right? Let's say the original array was something like 0, 0, 0, 1, 1, 1, 2, 2, 2. Okay. What happens is the last element, if we are choosing to remain, it can be 0, it can be 1, it can be 2, right? So if we choose 0, then the MX becomes 1. Otherwise, the MX will become uh, 0, right? So we can say that last value will be 2. Okay. Similarly, second last value will be 2. Similarly, we can say that the third last value will be 3. Basically, we're proving that from the back, it will follow this pattern like this, right? Until it reaches MEX, right? So in this array, the MEX is 3. So we can prove that the last will be like 3, 2, 1, like that it will be. And that's what we're proving right now. The last one is 1 always, because empty array, there's only one option. Then if there is 0 here, then this will become 2, right? MEX of this original is 3, right? And then we can take a 0 and 1. So the MEX becomes 2. Otherwise, we can take some other combination, 0 and 2, MEX becomes 1. Or we have 1 and 2, MEX becomes 0. So then 3. There are 3 possible options. And we can always show that let M equals MEX of array. Okay. Let M equals MEX of array. Last elements or suffix will be of the form MEX, then MEX minus 1, and so on until we get like 3, 2, 1 like this. So this second half of the array, we can say after the MEX point, like these last MEX elements, they will always be like this. And why will they always be like this? Because it's very simple to show. Let's say the array had unique elements. We're only writing unique elements. So let's say these are the unique elements of the array. Okay. The MEX of the array is 7, right? So we can show that in the end, it will look something like this. The last few elements will be something like this, right? And why will the last elements be like this? Because here we have no option but to choose empty array. So there's only one possible MEX. Here we can choose any element. So we can either make the element MEX equal to 0, or if we choose a 0, the MEX will become equal to 1, right? Now here we can choose 0, 1, 2 as possible MEX. And how we can do that? Because we can do two elements now, right? Two elements remain. So we can choose 0 and 1, then 2 becomes MEX. Otherwise, we can choose 0 and 2, 1 becomes the MEX. We can choose 1 and 2, and 0 becomes the MEX, right? So that's why there are three options here. Now we can say there are four possible options here. Why is that? Because we can choose three elements. So either we chose these three, MEX becomes 3, or we chose something like this, MEX became 0, right? Basically, whichever the MEX we want, we will just remove that element from the first four elements, distinct elements, right? So that's why the last ones will follow this pattern. Okay. I hope this part of the question is understandable. The last elements will be 1, 2, 3, 4 till MEX of array. Okay. So this is idea 1. Now, for what about the starting of the array? Okay. And we'll get to idea 2 now. Okay. Starting of the array. Now, let's say the array was 0, 0, 0, 1, 1, 1, 2, 2, 3, 4, 4. Then let's say 7, 7, 8, 8. Okay. This is our array. Now, 0 occurs 3 times, 1 occurs 3 times, 2 occurs 2 times, 3 occurs once, 4 occurs 2 times, 7 occurs 2 times, 8 occurs 2 times. MEX of the array is 5. MEX equals 5, right? So we can already say that from the back, the answer is going to be 1, 2, 3, 4, 5. And there's like a bunch of dashes for what the other answers will be, right? Now, how will we find the answers from the front? Okay. And the way we will compute the answers from the front is, if we are removing 0 elements, then there's only one possible answer, right? So A of 0 will also be equal to 1, correct? Answer of 0 will also be equal to 1. Now, what if we can remove one element? Okay. So let's say if there was two threes over here, right? If there were two threes over here, we can only remove one element. Well, we cannot affect any element. Even if we change this, remove one of these, it will not affect any element, right? So that's why the answer would not change in that case. But now there's exactly one 3 here, right? So if we remove this 3, then the new MEX becomes 3, right? And old MEX also is still possible. The old MEX is also still possible. If we did not remove the 3, then we remove some other element, right? So the number of possible MEX. So then A of 0 is 1, and then A of 1 will be A of 0. So the ones which were possible previously are still possible, plus number of elements with frequency 1, right? Number of elements less than equal to MEX with frequency 1. Why? Because now we can remove this from our array and make it an MEX, right? There's no point removing anything larger than MEX because MEX will always become smaller, right? So that's why it's number of elements less than or equal to the MEX with frequency 1. Now, what is A of 2? A of 2 is simply A of 1 because all the ones which are previously possible are still possible, right? Because the last 5 cases are already fixed. The last 5 cases will already be fixed, right? So in the last but one case, all the MEX will be possible, all the way from 0 to 1, 2, 3, 4, 5, right? In the last 5 cases, all the 0, 1, 2, 3, 4, 5 cases are held. So we can see that all the MEX possible previously will be possible. Simply just remove the excess frequency ones, right? Remove the two. So all the previous ones will be possible. But what will change is it will be A of 1 plus number of elements less than MEX with frequency 2. Okay. So what will A of 2 be? Let us see. A of 1 is simply 2, right? And then A of 1 is 2. And how many elements have frequency? 2. So 4 and 2. So these are the two elements which have frequency 2, right? And they are less than 5. These two elements are 4 and 2. They are less than 5. So there are two such elements. So here it will be 4. Okay. What about A of 3? A of 3 follows the same pattern. A of 3 equals A of 2 plus number of elements less than equal to MEX with frequency 3. Okay. And how many elements have frequency 3? This has frequency 3, this has frequency 3. That means that now that we can remove 3 elements, we can remove this fully, right? So now 0 is a new possible MEX. That's what the logic is. New possible MEX. Right? That's what the logic is. Okay. So what will this become? This will become what was A of 2? That was 4. And then again, there are two new possible ones here, right? And then this will become 6. What about A of 4? A of 4 will be A of 3 plus frequency 4, right? How many elements are frequency 4? There's nothing with frequency 4, right? So we can say that this also remains 6 plus 0, 6, and so on. And the answer for this test case, the answer for this given example test case will be 1, right? 2, 1, 2, 4, 6, 6, and then so on. It will keep remaining 6 until it reaches the last few elements where it will start decreasing, right? So it will start decreasing 5, 4, 3, 2, 1. And then this whole thing in the middle will be 6 itself, right? So these last elements we already fixed. When we reach them, we'll break the process, right? And then these last elements, we already filled them. And the starting elements will fill like this. And basically the idea is every time we can remove the whole new element, that means we got a new possible MEX, right? And what happens at this point, at this boundary, right? At this boundary, you can see that all the MEX are possible, right? 0, 1, 2, 3, 4, 5. Depending on which elements we removed, we can make any of the MEX of the array equal to any of those elements, right? So that's how this question works. Okay. I hope the logic was understandable. E is slightly harder, so 1400. Really? Yeah, okay, maybe 1400. Me seeing the number of solves, it's 1400 or more. Yeah, I guess idea 2 was a bit harder. But basically, it's like as soon as one element goes, right? As soon as we can remove all zeros, now we can make 0 the MEX. So we get a new MEX. Similarly, we can remove all 2s. So now we have a possibility of having 2 as MEX. So if you observe that, you will get this idea. In D, if someone can answer his doubt in D, then answer. Otherwise, at the very end, I will answer it, Ronak. Okay. So let's have a quick look at the code. So for frequency, we can just use a map, right? Although we can use unordered map, but I don't recommend unordered map in contests where there is hacking because, unordered map can be blown up. I think you should know this, right? It can be made into n squared if they give bad inputs. That's why I use normal map to count frequency, and the time complexity becomes big O of n log n. Let me just quickly show you the code, right? Code for this problem. The code is not that bad actually. Code is pretty short. I don't know why I was remembering this question is hard. Anyways, so we have a map. Each element, we count its frequency. Okay, so this is like the frequency map. Now we're going to have a second map, okay, which is going to be like, so the second map will be like for a given frequency, f, how many elements have that frequency, okay, have that frequency. Okay, so this is what the second map stores. You can see why we are storing this, because that is what we're adding over here, right? We are adding frequency of 3, like how many elements have frequency of 3. And we can see that zeros have frequency of 3 and ones have frequency of 3. So that's what we're counting in the second map, okay? So basically, this is the element and this is its frequency, right? So what I'm going to do is I'm going to count that this element has frequency of y, correct? Also, this should be only for elements less than or equal to the max, right? Less than or equal to the max. That's why side by side I am making the mx, like I have a variable of max where I'm finding the max, right? So I'm doing both at once. This is doing both at once, finding and incrementing the max, and it's also making the frequency map, making frequency map, ensuring elements larger than mx don't get in the map. Okay, don't get in the map since we only care about elements less than equal to max. Okay, so this is what these two lines are doing. Fine. Now what? Now this is the step from the back, right? An equals 1 and till n minus mex. So this is for the last few elements. This is idea 1, right? The last few mex will be like 1, 2, 3, 4 till mex. So that I will simply do ai equals ai plus 1, right? So that what does that mean? That means like um, 2 is 1 plus 1, right? 2 is 1 plus 1, then 3 is 2 plus 1. So that's what I'm filling from the back. Okay, that's what I'm filling from the back. Fine. Now from the front, what will I fill? Uh, Sorry about that. From the front, what will I fill? A of I equals the previous element plus frequency at I. So how many elements have the frequency of I? Right? The frequency, how many elements have frequency of I? So I'm adding that much amount to A of I minus 1. Right? This is the same as idea 2, what process we did, is equal to the previous element plus the number of elements with the frequency of I. Okay. And I have written this additional line. If A of I break, so if we come across this last portion which is already filled, we can just break. Okay. Then we finally print all the elements A of I out. Fine. Does that make sense? Rating of this problem, I think, will be 1400. How to compute MEX from array? Okay, so I'll tell you how to compute MEX from array. How to find MEX? I think this is Googleable. It's a very standard problem. But once you sort the array, once you sort array, okay, and let's say you have like 0, 0, 1, 1, 2, 3, 4, 7, 8. Okay, then you can simply write the following loop: MEX equals 0. Then for each element X in A, okay, so let this be A. If X equal to MEX, then MEX plus plus. And this much code will find you the MEX of the array. Okay, this will find you MEX of the array. How does this work? It's simple because at start it's saying 0 is missing. Okay, and then as soon as it finds the 0, it becomes 1 is missing. Right now 1 is missing. Then it reaches 1. Okay, now it found a 1. It's like, okay, now 1 is there. Now 2 is missing, right? Because MEX is the smallest number which is missing. That's why this code works to find the MEX. You use difference array. Okay, I have no idea how to do this with difference array. Obviously, there'll be other solutions. I think there must be simpler solutions since a lot of people solve this. Yeah, so here also I'm finding MEX on the fly. In the map, all the elements are stored sorted, right? So in a map, it's already stored sorted. So if X is equal to MEX, I'm doing MEX plus plus. As you can see, it's the same thing. If X equals MEX, MEX plus plus, all elements in map are already stored in sorted order. So that's why this code computes MEX and it increases the frequency only for the elements which are less than or equal to MEX. Okay. Binary search. I have no idea if that works, but okay. Obviously, there'll be many approaches, yeah. You found lower and upper bound and binary search to find. Okay, that is interesting. That is interesting. All right. So that's it for problem E. We'll move on. Two questions are left, F and G. Okay, problem F. I'll just quickly go drink some more water and come back. Problem F. So F is again a very constructive problem, guys. Like I made a guess pretty quickly. It became correct. The way I'll approach this is I'll show you some of the guesses I made, and I'll show you the correct guess. Like it's constructive, so first you make the guess and then you write the proof. At least that's how I solved this, right? I made the guess, then I proved it afterwards. And I'll take you through my thinking process step by step, how I solve this question. Okay. Call a permutation P of length n good if GCD of P of I, comma I is greater than 1. Okay, so the GCD of I, which is the position of the element, and the value at that element should be greater than 1. Okay. Find a good permutation with the minimum number of fixed points. What is fixed point? A fixed point is a position where P of I equal to I. Okay. So at position 2, if the value is 2, then that's a fixed point. If there are multiple such permutations, print any of them. If you use sieve, interesting. I did use sieve, not exactly sieve. I used a pretty different approach, but it was also pretty simple, I think. My approach was also pretty simple, I think, for F. Okay. So let's take an example and try to understand what it means. Okay. So let's take 6 as our input. So n equals 6. And we need to find permutation such that as many possible like GCD of P of I, comma I should be greater than 1, right? For 2 less than I less than equal to n. So it must be true for 2 less than equal to I less than equal to n with minimum fixed points. Minimum fixed points. Okay. And to be honest, my proof for this is not that great. So you will need to bear with me a little bit. But yeah, it's a constructive problem. So they usually are like that. Example 1, n equals 6. Okay. And obviously one solution for n equals 6 is to write 1, 2, 3, 4, 5, 6. Okay. This is one idea we can write. Obviously, one thing you should observe is since this needs to be true for 2 to n, right? So the value of 1 should always go at position 1. This is for sure. 1 should be always at position 1. In all the answers, you can see that is true. See here, 1 is at 1, 1 is at 1. Why is that? Because GCD of any number with 1 will be something else, right? It'll become 2. It'll become GCD of any number with 1 will be 1. So it can't be greater than 1. So yeah, the first element should be 1. Okay. This is so very trivial. First element should be 1. Should be 1. Okay. Now let us take the example where all the points are fixed points. Okay. Now here we can see GCD of 2 and 2 is 2. GCD of 3 and 3 is 3. Right. But the problem is everything is a fixed point. So while it is satisfying a condition, everything is a fixed point and we don't want that. Okay. So let's try to do something. Let's try to swap 2 and 4. Okay. And what will happen is now this will become GCD of 4 and 2, right? So value is 4 and index is 2. So GCD of 4 and 2 is 2. So this is not a fixed point and it's also satisfying the condition. Perfect. Here again, it will become GCD of 2 and 4. Value of is 2. This thing is 4, right? So now both of these are not fixed points and the condition is also satisfied, right? What about 3? Let's swap it with 6. Okay, we'll swap it with 6. Now we have 6 here, 3 here. Now GCD of 6 and 3, right? Position is 3. This is I. This is P of I, right? This is 3, which is greater than 1, correct? So we can say that this is not a fixed point and it is satisfying the condition. Okay. This is still a fixed point and this is not a fixed point and satisfying the condition. So we can say that minimum 2 fixed points will be there, right? This will be 1 fixed point, 2 fixed point. So minimum 2 fixed points will be there, but rest of elements we swapped in such a way that, it satisfied all the conditions. And we can see that this is the same answer. 1, 4, 6, 2, 5, 3, 1, 4, 6, 2, 5, 3, right? For n equals 6. So, okay, so I'll tell you how I'll approach this. Okay, I'll give an idea. I'll try to see if that idea works. If it fails, we'll try a new idea. And actually, that's how you solve constructive problems. Okay, so it's like scientific method, right? Hypothesis. You have a hypothesis, you test the hypothesis. If it doesn't work, you try another hypothesis, right? So my first guess is, I'll call these guesses. Okay, guess one. This is how I approach the problem in the contest. And I think many people, even up to CM master rating, will approach it like this itself. So I think, you know, like the brain, like you can't always solve everything with deduction. Sometimes you need to make a guess and then do induction, right? From that guess. So yeah, let's get into it. So my guess is, can we always try to swap like A of I and 2 times A of I, right? So like if you see in this example, we swap 2 and 4, right? And we swap 6 and 3. So I thought, what if can we always do this? Can we just swap 2 and 4, 6 and 3, 5 and 10? Like that, can we do it and solve the question? Okay. So this was my guess. And why am I guessing this? Because see, GCD of 2 and 4 will always be 2, right? So it'll be greater than 1 in both the cases. So I thought, is this possible, right? Let us try for n equals 10. Okay, what happens? Well, let's try for n equals 13. They already gave us n equals 13, so we can check our answer right here itself, right? So you can see that n equals 13, luckily they gave for us. So we can check our answer. In n equals 13, how many fixed points do they have? They have, see, this is not a fixed point, it's not a fixed point. 7 is the first fixed point, like 7, then 11 and 13, and 1. So total 4 fixed points they have, right? 4 fixed points. We should somehow make it also 4 fixed points because that's the minimum number of fixed points, right? It's already given in the test case. So I swap 2 and 4, right? And I swap 6 and 3. Then 1, 2, 3, then 4 is to 2. 5 I, let's say, swapped with 10, right? 5 I swapped with 10. Then 6 I swapped with 3. 7 I have nothing to swap with, right? 14 is not in the array. So 7 will be a fixed point. Here also 7 is a fixed point, as you can observe, right? Now, what about 8? Okay, now 8 comes to a trouble, okay? There is no 16 in the array, so I can't swap it with 2 times 8, correct? And unfortunately, 4 is already occupied, right? 4 is occupied, right? Like 4 already went off here, right? But what if I just swap anyways? What if I swap this 2 and this 8? Okay, will this satisfy my condition? 8 and 2. I just swapped with whatever is at the position of 4 I swapped, okay? Now see, because 4 and 8 share a common factor and 2 and 4 share a common factor, then all of these will share common factor, right? So we can say that GCD of 2 and 8 is 2, which is greater than 1. So the property is still working. This property is still holding up. It seems like maybe our guess could be correct, right? What about 9? Now the thing is, 18 is not in the array, right? So we can't swap it with that. What about 9 by 2? Well, 9 is not even divisible by 2. So there's nothing to swap with 9. So it looks like 9 will be a fixed point, right? But look at their answer. Their 9 came here and their 3 came in the position of 9, right? So for them, 9 was not a fixed point, right? So that means our guess is wrong. This guess was wrong. Okay? Like we simply cannot swap with A of I 2 times A of I because the thing is there's nowhere for 9 to go in this example, right? Because 9 by 2 is not even a number and 2 times 9 is not in the array, so there's nothing for 9 to go. Okay. Is this fine? Me teaching with like guesses. I hope it's fine. If I directly tell the answer, I think you'll not be able to understand how the answer came. You'll be like, how did this answer come? That's why I'm telling all the guesses I thought first. Okay. So then I made my second guess. Okay. My second guess was, what if we swap 9 with 3, right? Like they also swapped in the example 9 with 3, correct? They swapped 9 with 3. So my second guess is, um, swap with your smallest divisor. Okay. Just swap with like smallest divisor. And what we'll do is we'll go from back to front. Okay. Like, uh, 12 का smallest divisor is, um, like smallest available divisor will swap with. Okay. So for example, 9 का smallest divisor is 3. So I'll swap 9 and 3, right? Similarly, 8 का smallest divisor is 2. So I'll swap 8 and 2 like that, and 4 and 2, so on. And I'll do this backwards, right? Like, so that was my idea. Like 9 I will swap with 3, and then, sorry, 8 I'll swap with 2, so on. I'll try to swap like that, and I'll do it backwards. So this was my second guess, okay? Unfortunately, this even fails for I think 1, 2, 3, 4, 5, 6. This idea will fail. And the reason is, 6 has the smallest divisor 2, right? 6 has smallest divisor 2. So these two will swap. Okay. Now 5 does not have any divisor, right? So 5 cannot swap with anyone. It remains a fixed point. Now 4 has the smallest divisor here, right? So what happens is 4 goes here, 6 comes here. Now till now everything is fine. But what about 3? Now 3 has nothing to swap with. Okay. 3 has nothing to be swapped with. And that's why 3 becomes a fixed point. And we know that, for this case, only 5 was fixed point. Okay. So that's why this guess also failed. Guess failed. Okay. Uh, right. So swapping with smallest divisor didn't work. So after this, I got an idea. Okay. Like we're doing this backward swapping thing. Uh, we are doing this backward swapping thing. Why not? Why not swap with your largest divisor? Okay. Swap with your largest divisor. Each time we go from back to front and we will swap with our largest divisor. And in fact, turns out this is the correct answer. At least this is one of the ways to get the correct answer. Okay. And I'll show you why it is correct answer and how it works for the test cases first. Okay. So first we'll try with 1, 2, 3, 4, 5, 6. Okay. 1, 2, 3, 4, 5, 6. So we start at element 6. Largest divisor of 6 is 3. Correct. So we swap these two and we get 1, 2, 6, 4, 5, 3. As you can see, since we're swapping with divisors, there will be a GCD, right? There will be a common divisor greater than 1. That's why we are doing this, right? GCD will be always greater than 1 since we're only swapping with the divisors. And where the fixed point thing also stays because we're swapping the number off, right? As soon as it has a divisor, we'll swap it off, right? Now 5 does not have any divisor other than 1. Leave it. 4 has, largest divisor of 4 is 2. So we swap 4 and 2, right? Now 3, like this is position 3, right? Position 3 has no other divisors, so we don't swap this, and we are done. Now you can see for test case 6, we're getting the correct answer, which is 1, 4, 6, 2, 5, 3, right? So test case 6, of n equals 6, we solved. Let us try n equals 13, okay? So we have the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 is prime. It has no divisors, nowhere for it to go. Okay. 12, what is the largest divisor of 12? Well, that is 6, right? So I will swap 12 with 6, and what happens? I get 12 here, and I get 6 here. Okay. 11 is prime, we can't swap it. 10 has largest divisor 5, so we swap it with 5. Okay. 9 has largest divisor 3, we will swap it with 3. Okay. 8 has largest divisor 4, so we swap it with 4. 7 is prime, it has no divisors. So 12, this is not 12 actually, this is 1, 2, 3, 4, 5, 6, right? So 6 has largest divisor 3. So we swap it with 3. The values will swap with 3, okay? The value of 6 will be swapped with the value of 3, okay? Now 5. 5 has the largest divisor 1, right? 5 is prime, so no swapping here. 4 has largest divisor 2, so we swap it with 2. And this is our final array. And in fact, you can see the number of fixed points is the same as the question. There are 4 fixed points, 1, 7, 11, and 13. And this method seemed to work. Now that we have gotten the idea, right? Now that we got this idea and it seems to work for the test cases, now we will try to find the proof. And actually, I know this is hard, but with practice, you get good at guessing, right? This is how I did it. You get the proof later. Now I can show you proof that this always works. So obviously, once I got this method, I tried to prove it and I was successfully able to prove it. So I coded it out. Proof that this works. Okay. And what is our idea? First, we'll just summarize our idea. Summary of the idea is simply from back to front, right? From n to 1, from n to 1, I equals n to 1, swap a of I with a of, let's call largest divisor of I, LD of I, LD of I. And this is our idea, right? From I equals n to 1, swap a of I with a of LD of I. Obviously, if LD of I is greater than 1, we don't want anything to swap here, right? We don't want prime numbers to start swapping to the first position. So if LD of I is greater than 1, then we do this, okay? So LD of I should be greater than 1, and we'll do this. Now let's prove that this works, okay? How do we prove this? Well, if the current number, okay, let's say we are at this number and we swap with a smaller number. What happens? We get a number which is smaller than me and which also is a common factor with me, right? Because it's my largest divisor. So obviously it shares some divisor with me, right? So that's why my GCD will be this number itself, right? So my GCD will be greater than 1. So that's why this number is getting fixed, right? Similarly, if this number, right, if this number is getting its divisor coming here, this one is also getting, like, it's not becoming a fixed point, right? And what if I had no divisors, right? What if I had no divisors to swap with? In that case also, if I was like 7, if I had no divisors to swap with, in that case, there's nothing else to do here because I can't swap this side. And it means that nothing swapped with me also. If nothing swapped with me, that means that even 2 times 7 was not present. Otherwise, 2 times 7 would have definitely swapped with me. 3 times 7 was not present. Otherwise, 3 times 7 would have definitely passed with me, right? So that's why you're a prime number and there is there's no 2 times 7, there's no 3 times 7, there's nothing like that. Right? There's no k times 7 in the array. So basically what our method is ensuring is that for each AFI, if k times AFI existed, right, then and you were its largest factor, right? You were largest factor, like um, AFI was the largest factor of that k times AFI, you would have been swapped, right? And as soon as, like, for example, 2 times AFI exists, you will be swapped with that value. So like this is the rough proof of that, right? Um, this is the rough proof of the idea. Basically, the proof is in 2 steps. One, if I have a largest factor, so I'll call that LD of I greater than 1, swapping fixes both me and LD of I, right? Fixes both I and LD of I. So that's why I should do the swap. Similarly, um, if I have been swapped, right? If I have been swapped, I'm already fixed, right? I'm already fixed. So I don't need to worry. I can obviously do further swaps because my specific I value is gone. So that's why I can't ever become a fixed point anymore, right? Because my specific value of I, it has gone front in the array, right? So I can't become a fixed point anymore. basically the value of I is getting shifted further in the array, so you cannot become a fixed point anymore, right? So you can participate in further swapping if needed, right? Participate in further swapping if needed, right? Now, to complete the proof, if I could not have swapped, if I didn't swap with anyone, right? With anyone, and my largest divisor, like I'm a prime number, so my largest divisor is 1, right? Then there is no way, there is no hope, there is no hope. I'll always become a fixed point, right? And we can see this in the examples itself. Um, like, for example, 7, it has no one to swap with, literally no one to swap with. There's no 2 times 7, there's no 3 times 7. You can't swap with anyone, right? And the final step is to show that if I had any multiples present in the array, right? Present in the array, like if I had 2 times a of I, 3 times a of I, so on present in the array, I will have been swapped. I will have been swapped. So that means that every element which could have been swapped has been swapped. This is the main idea of the proof, like kind of completeness. So it's not a very formal proof, like I'm not writing like in formal math or anything, because that will take time plus energy, and I don't think that will be very instructive either. For that, probably the editorial will have a very nice proof or something like that. So yeah, this is the proof of this idea. So now let's write it as an algorithm. Algorithm. Uh, First, for each value, so how much can I go up to? You can see that I goes up to 10 to the power 5, right? So for each I from 1 to 10 to the power 5, store its largest divisor. Store its largest divisor, right? And then second thing we can do is, and we can do this in n root n, because we can go through all the divisors in root n, right? So we can find its largest divisor. Now, for each test case, for each test case, um, input n, right? Input n, make the answer array equal to 1, 2, 3, 4 till n, right? From back, um, swap um, swap a of I with my divisor, largest divisor of I. And then finally print values of a. Finally print a. And the overall time complexity for this is big O of n root n pre-processing plus so since n is stable over the sum of test cases, so it's n root n plus big O of n. Since the swapping process is only big O of n, right? So it's big O of n root plus n plus n. I'm sure there'll be some solutions with sieve and all, so that might become n log n plus n, something like that. But this is the solution I found. Each time if you swap which is largest divisor, then you can ensure that everything which could have been swapped has been swapped, and everything which which could not have been swapped is not touched, right? And since we're swapping larger animal with the smaller one, once your value goes in front, it can never become a fixed point again. So it can participate in further swaps. So yeah, that's the idea. We took like 1 or 2 guesses which failed. We took a third guess, like build it upon our previous guesses, right? And then that guess was working, so we tried to prove it. We could successfully prove it. So we wrote the algorithm down, thought about the time complexity, and then we'll code it. Okay, let's see any doubts or what other solutions other people have. You used prime and then shuffled. I guess shuffling and all works, but I didn't want to do the shuffling thing. Like shuffling seems a bit complicated. I also thought about shuffling, right? Like make a graph type of thing for each element and what it divides, and then try to shuffle it. But I was like, nah. Smallest divisor and swap with it. Then find, yeah. I suppose that would work. Yeah. I guess you could try to make it work. Let's see. Do try and submit afterwards. If you have any doubts and you're in TLE, then you can just make a doubt, right? Or you can put in YouTube comments. I may or may not check it. Let's see. So how to implement this? First, we find the largest factor. So I wrote it as largest factor, LF, for all the elements till 10 to the power 5, right? So this is just a pre-computation. It's always fixed 10 to the power 5 root 10 to the power 5. For each element, we find its largest factor and we just store it in this array. Then for each test case, we make a vector of n. Each value of vector of I will be equal to I. If largest factor is 1, we continue. Otherwise, we swap I with largest factor of I. Finally, print the output. Simple direct implementation of our idea, right? Direct implementation of this idea. No sieve and all required. Although you could say that this is something similar to sieve. We're finding the largest divisor of every number. I guess you could optimize this also a little bit. N root n passes the constraint, so that's why I wrote it up and it was simple to write. Okay, if there are no doubts in F, we'll move on to problem G. Problem G, I guess, was hard. I would say 2000 rated, maybe 1800 to 2000. Maybe even more, I'm not sure. After that, if it's not too late, we'll do some general doubts. Any doubts with F? Ask now. Otherwise, we're moving on. Okay, moving on to problem G. I guess this will be pretty hard for most of you, but I'll try my best to explain it. I think you need to be at least like 14, 1500 before you can start getting the solution for G. So don't worry if you're not getting it right. You're given an integer m and an array A containing non-negative integers smaller than m. Answer the following queries. The first type of query is ix. Assign a of I equals to x. So very simple. We're just doing updates, right? We're taking one element of the array and changing it to some other value, right? So a of I equals to x. Then the second operation is 2k. In one operation, choose an element a of I and assign a of I equals a of I plus k mod m. Okay. So k is given over here. Mod m was given in the start of the question, and we can change a of I to a of I plus k mod m, and as many times. So 0 times or more than 0 times operations, we can do this. And note that instance of query 2 are independent. No actual operations are taking place. Instant of query 1 are persistent. Okay. So we basically need to maintain some kind of invariant property, some kind of data structure. These questions are usually like 1018, like 1800, 2000 higher. It's a very standard looking question for that rating, I would say. Okay. So let's just explore maybe one test case and see how it works. So initially our array for the first test case is 7 elements, and then the second value is I think mod value, right? So the mod value m is 6. Number of queries is 6. What are the elements of the array? The elements are 4, 5, 2, 2, 4, 1, 0, right? Okay. All right. Now what's the first query? So let's just write query number 1. Okay. Query number 1. And what does the query ask of us? Again, we can see NM are like the usual 10 to the power 5, 10 power 5. So yeah, it has to be. Oh yeah, one thing. Sum of m over all test cases is not guaranteed, okay? The mod value m, sum of m over all test cases is not guaranteed. So be careful about that, guys. Okay, we can't iterate over m itself. Fine. Yeah. Okay. So the first query simply says 2, 4. So it's query of type 2 with 4. What is query of type 2? We can choose any element, and as many times as we want, we can do AFI plus K mod n, right? And what we can basically do is we need to make it sorted, right? We need to make it non-decreasing order. We need to make this sorted using this mod operation, okay? So let's try to see for one number what all numbers we can get. So from 4, what are the possible numbers we can get from 4, okay? So we can either keep it as 4, right? Either keep it as 4, or we can do 4 plus 4 mod 6. What is 4 plus 4 mod 6? Well, that's 8 mod 6 or 2, right? That's 8 mod 6 or 2. Now, what is 2 plus 4 mod 6? Well, we can see 2 plus 4 mod 6 is again 4 itself, right? So 2 plus 4 mod 6 is, sorry, 2 plus 4 mod 6 is 0, right? Because it becomes 6. Now 0 plus 4 mod 6 is 4. So it becomes like cycle 4, 2, 0, 4, 2, 0, 4, 2, 0. So using this operation, the only values we can set it are 4, 2, and 0, right? And we want to make it sorted. So I'm going to set it to the smallest possible value. Okay, I'm going to set it to the smallest possible value, which is 0. Fine. Now I will try 5. What are the possible values for 5? Well, if you see, I think these are, I'm not exactly sure what this is called. This is a number theory concept, that much I remember. But yeah, it's something residues respect to a modulo. I'm not very sure if that's the correct concept, but this is a slightly higher number theory concept. Basically, what numbers we can form if we keep adding some k mod n. It's a well-known thing. I've seen it in other problems as well. Now 5 we get 5 plus 4 mod 6, 9 mod 6. That's 3. 3 plus 4 mod 6, 7 mod 6. That's 1. And then 1 plus 4 mod 6, that's 5 mod 6. Again, came to 5, so we again cycle, right? So these are the possible values for 5, okay? What's the smallest? 1 is the smallest here. So we'll try to make it 1. Now what about 2? Again, 2 has the following options, 2, 0, 4. Since that's it's like, I think, I'm not sure, is it called residue or is it called congruence class? Something like that it's called. I don't remember. It has something to do with those number theory stuff. Anyways, so in this also we can see that 2, 0, and 4 are the possible options for 2. It needs to be in sorted order, so it can't be 0. So we'll make it 2. Similarly, we'll leave this one also as 2. Here it's 4. So 4 can be made into 4, 0, or 2. It needs to be in sorted order, so we'll make it 2. Now 1 can be either 1, 3, or 5, right? As you can see, it can be 1, 3, or 5. We can't make it 1, so we'll make it 3. What about 0? 0 can be 0, 2, or 4. We can't make it 0 or 2, so we'll make it 4. You can say yes, yes, we can make it in sorted order. So the answer is yes over here for this test case. Okay. Now, what is the second query? The second query simply changes one of the elements, right? It takes the element at position 4. So it takes this and converts it to a 5. Okay. And then now it's like, now you do it. Okay, now you do it. And okay, let's say this became a 5. Okay. So after the second query, and the first type of query is permanent. Okay. The first type of query is permanent. So now it's permanently 5 in the array itself. Okay. Now what happens is, so let's say the first 3 steps are the same. Okay. The first 3 steps are the same. But now 5 is in this congruence class or whatever you want to call it, in this set of possible values. So it can't become 1 because it must be in sorted order. So this becomes 3. Now what about 4? 4 is in this set. It can't be 0. It can't be 2 since it's sorted order. Becomes 4 now. Now what about this 1? It has to be 1, 2, or 3. Sorry, 1, 3, or 5. And 1 is not possible. 3 is not possible. It becomes 5. Now it comes to the 0. Right? Now 0 must be 0, 2, or 4. But even if it is 4, it will become smaller than 5, right? So it can't be in sorted answer. So that's why the answer becomes no to this query. Okay, so here also we have 2, 4. Here also we have 2, 4. Earlier it was possible, but when we change this element to a 5, now it's no longer possible, right? That's why it's yes over here, no over here. So I hope this explains what the question is asking. Okay, why are you spamming Dhruv? Please do not spam. Yeah, I will explain what I'm not sure what exactly this property is called, but yeah, I will explain the whole problem very nicely in detail. Dhruv, I don't know what you're trying to say. Please don't spam, otherwise I'll have to kick you out or something. I've not done that before, but there is a nice timeout or ban button. So yeah. Okay. Anyways, so we'll break this problem down. Okay, it's a very logical problem. There's no guessing over here. We'll break it down step by step and take it step by step. Okay. Um, so now first observation, right? And what we're going to do is in the first observation, given a value of m, a value of n, and a value of k, right? What are the possible values AI can reach? What are possible values AI can be? And actually, if you study, this is a very theory. This is math, number theory. Okay, it's a very standard number theory idea. I don't know the name, but I guess I should Google it afterwards. But yeah, I don't know the name of this idea. I've seen it before. But even if not seen it, I think it's doable within the contest time. Like if you had already solved the previous questions, you could think of this during the contest. What are the possible values some A of I can be? Right. So we have some value of K, we have some value of M. Okay. So it can stay A of I, or it will become A of I plus K mod M, right? Or it will be A of I plus 2K mod M, right? Because we added K twice, right? Like going A of I plus 3K mod M, right? A of I plus 4K mod M, right? So on and so forth. So what are the possible values this can be? Can they be all the possible values? Clearly, they can't be all the possible values since we saw earlier that it was not being all the possible values, right? See here, it's not being all the possible values. 4 can only go through 4, 2, and 0, they form a cycle. 5 can only go through 5, 3, and 1, and they form a cycle, right? So how does this work, right? And I'll tell you the answer to this. It's a bit of theory. To do it yourself will take some time, but and I don't remember the proof exactly. But I'll write this in green, I suppose. And the answer is um, if M and K, I think this is their popular concept in cryptography as well. In cryptography, while choosing cipher like keys and stuff, they do this. I do not remember why. If M and K are co-prime, then AI can be any value in 0, 1, 2, M minus 1. Okay, it can become any value. If M and K are co-prime, we can change A of I to any value. Okay, and if they are not co-prime, that means they have some GCD, right? They will have some GCD, right? So they will have some GCD if not co-prime. If not co-prime. So I'm just telling you this as fact, I think. If not co-prime, then let G be the GCD of M and K. Okay. Then the values of A of I will be everything uh, which leaves the same remainder, which leaves, I guess you can show this with like Euclid's like that GCD algorithm also. I think you can prove it with that. I'm not sure. Which leaves the same remainder with G as A of I. Okay. So basically it's all the values X. So how to write this in math terms, right? I want to write this in math terms. It's all the values X. It's all the values X such that 0 is less than X less than equal to M minus 1 and X equals to A of I mod G. Okay. And this is the Like, I guess this is a number theory fact, which you're expected to know to solve this problem. But even if you don't know, I guess you could, like, I don't think you can prove it on the spot, but you can see the pattern maybe. And I'll show you why this happens. Okay. Let us take our old example itself. K was 4, and well, let's take K equals 2. Okay. M equals 6, K equals 2. Okay. Now let's say we have 1. Our current value of A of I is 1. Okay. A of I is 1. What happens to A of I? Well, if we add 2, then it becomes 3, right? And so the possible values for A of I become A of I is 1 in the start, so it can be 1, it can become 3. We add 2 again, it becomes 5, right? Now we add 2 again, and it warps back around and becomes 1 again, right? So it becomes in this loop 1, 3, 5, 1, 3, 5, 1, 3, 5, so on, right? Similarly, um, if we had 0, right? If A of I was 0, then we add 2, it becomes 2. We add 2, it becomes 4. We add 2, it becomes 6, which is 0. Then again 2, 4, 0, 2, 4, 0, 2, 4. And that's what happens to A of I if it started somewhere here, right? And the reason for this is, you see GCD of K and 6, right? That is GCD of 2 and 6. That is 2, right? 2 is the GCD of 2 and 6. And what happens to that is the value mod 2 never changes, right? Because currently the value is 1, right? If you add a 2, then mod 2, the value will not change, right? The mod 2, the value will not change, right? So it'll become 3, and then mod 2 again, the value will not change, become 5. And then it wraps around 6, it will still remain the same mod 2, right? Because 2 divides 6, because 2 divides 6, when it wraps back around, it will still remain the same value. Now let's see an example where they're coprime. Okay, let's see an example where they're proprime. So let's say M is 7. Okay, now GCD of 7 and 2 is 1, and we'll see that all the values become possible. So let's start at 0. Let A of I be 0. We add 2, it's 2. Add 2, it's 4. It's 6. Now we add 2 again, right? And it will become 1. Why will it become 1? Because 6 plus 2 is 8. 8 mod 7 is 1. Because 7 is not divisible by 2, 7 is not divisible by 2, it wraps back around, but it does not become 0 while wrapping back around, right? It has this, it becomes 1. So now it becomes 1. It goes to 3. It goes to 5. It goes to 7. So that goes to 0 again, right? So you can see that the pattern is 0, 2, 4, 6, 1, 3, 5, 0, 2, 4, 6, 1, 3, 5. You can see that all the numbers from 0 to m minus 1 are there, right? So this is the key idea. If they are coprime, then you can make A of I into anything you want. If they are not coprime, then we are limited to only this. Like each element is limited to its congruence class or whatever, which is respected to mod of G, A of I mod G. Okay. So I hope this is understandable, right? Guys, if you can understand, just please put in the chat, right? Like, even if you did not understand the proof, at least you know this new fact now. It's a number theory fact. Keep it in mind, right? Now, the interesting thing we already saw, and the interesting idea which we get from this, let's call this idea one. So this is just fact one, right? This is fact one, I guess. Idea one is, if for some query M and K are coprime, right? If M and K are coprime, then you know what happens? Very simple thing happens, and that is answer is always yes. And why is it always yes? Because if they are coprime, we can make any number into any other number. Correct? We can make any number into any other number because this kind of a situation happens. 0 becomes 2, 2 becomes 4, 4, 6, 1, 3, 5, and it cycles back around. So we can just go around this cycle. We can make all the numbers equal. Once all the numbers are equal, we can make all the numbers 0, right? And then it will be sorted, right? So for coprime cases, the answer is directly yes. Okay. I hope that's understandable. And this is amazing for us. And why is that? Because um, it already eliminates a lot of chunk of possibility, right? It just makes it straight away yes. Now the second idea is idea two. In the cases where they're not coprime, we take GCD of M and K, correct? So we only care about GCD G of M and K, right? G equals GCD of M and K. Now, obviously, G is a factor of M, right? It's the greatest common factor. So G is a factor of M, right? So that's why we only care about factors of M. And what do I mean by this? I'll tell you later, actually. I'll explain the question a bit more and explain what this means. But we only care about factors of M, and that will help us a lot, okay? So just keep this in mind that the factors of M are very important. I'll understand what we mean by only care about it. Okay. Now going back to our original array, I'll show you one interesting thing. Okay. Going back to our original array, we have 4, 5, 2, 5. Okay, original array was 4, 5, 2, 2, 4, 5, 2, 2. Now we're going to make some more observations to help us solve the problem. The original array was 4, 5, 2, 2, 4, 1, 0. What was it? Yeah, 4, 1. Let me just go see the problem itself. 4, 1, 0. Yeah. Okay. So now we know that for our first query, m equals 6, k equals 4, right? And m is already pre-decided in the question itself. Like m is given before all the queries, k is given with the query, right? So we can say that GCD of m and k is 2, right? So we only care about values mod 2, right? We care about these values mod 2, okay? Like we just saw the equivalence class thing or whatever it's called demonstrated, right? So we take all the values mod 2. This is 1 mod 2. Sorry, this is 0 mod 2. This is 1 mod 2. This is 0 mod 2, 0 mod 2, 0 mod 2, 1 mod 2, 0 mod 2. Okay, this is what comes out. And the interesting thing here is, if you observe, the zeros, they can be any of the values which are 0 mod 2, which is 0 to 4. And the ones, they can be any of the values which are 1 mod 2, which is 1, 3, 5. And that's what we saw above, right? We saw that the possible values for this are 4, 2, and 0. The possible values for this are 5, 3, and 1. And that's what we have now understood why this is happening. We have understood why this is happening. It's happening because of this fact, right? It's happening because of this fact. And we saw like brief like logic behind this. So basically we can just take the GCD, we can mod the entire array with that GCD, right? And we can say that this also has the option of being some error with the pen, just a second. Yeah, okay. This also has the option of being only 0 to 4, right? So all the zeros can be any of 0 to 4. All the ones can be any of 1, 3, 5, right? That's because mod 2, they are different, right? And this is their equivalence class, basically. I'm not exactly sure of the exact term, so I might be butchering it very badly. But yeah. So now the interesting thing is, since this is a 0, 1, now there's a drop over here, right? So this is one chunk, this is another chunk, and this is a third chunk, okay? So what we can say is, we fill the smallest values here, 0 and 1. Then this chunk, we fill the other values, 2, 2, 2, and the 3 from this one, right? And then here we can fill a 4. right? If there was another 1 over here, we could fill a 5, right? And what if the array was something like this? 0, 1, 0. Okay. In this case, it would not be possible. Okay. In this case, it would not be possible because now we filled a 5. Now again, we have a 0. And now we cannot do anything. There's no 6. It's only 0, 2, or 4. And now we get into decreasing, right? So basically, in this array, where we have done mod with GCD, where we have each element mod with the GCD, count how many blocks, how many sorted blocks are there. Okay, count how many sorted blocks are there. If the number of sorted blocks, okay, if the number of sorted blocks is so here we can see that the number of breakpoints in the blocks. So there's one breakpoint. Here's a two breakpoints. So in that case, it was yes. But as soon as there was a third breakpoint over here, right? As soon as there was this third breakpoint over here, it became not possible, right? So if aka breakpoints like it went to 0, 1, then it dropped back to 0. So that's what I mean by break. Like if it went 0, 1, 2, like so on, if it was increasing, then it's fine. But here, 0 and 1 are the only values, and it's kind of like we're dividing into sorted blocks, right? If instead of GCD being 2, if the GCD was 3, then 0, 1, 2, and this would be one block. And then if it dips, then it's another block, right? So we count all the sorted blocks in this. And if there are less than m divided by GCD, so m divided by GCD blocks, breaks, not blocks, breakpoints, the points where it becomes unsorted, like there's an inversion over there, inversion point, we could say it. Answer is yes. So answer will be yes. Otherwise, answer is no. Okay. So what we are doing here, we are taking the array, we are taking it mod GCD of m and k. Okay. And once we have taken mod of that, we need to know if there are less than m by g breakpoints or greater than equal to m by g breakpoints. If they're less than m by g breakpoints, we can see that we can fill all the elements, right? So again, I'll give another example. Let me take n equals 9, and let's take n equals 12, k equals 3. GCD is 3, as you can see, GCD is 3. Okay. Or we can take k equals 9 also. So now also GCD is 3. Okay. So now what we can basically say is if the array we take mod 3, right? So we have 0, 0, 0, 1. And then 0, 1, 2, 3, right? How many elements are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we can have one more element, right? Now you can see the number of breakpoints. The number of breakpoints here are 1. Then here's a second breakpoint. Here's a third breakpoint. And now 12 by 3 equals 4. Since 4 is greater than 3, the answer is yes. If there was even one more breakpoint, if there was one additional breakpoint somewhere, like I changed this to a 1 over here, right? And here it's breakpoint because this is a sorted block, sorted block, sorted block, sorted block. If there was an additional breakpoint, now the number of breakpoints is 4, and the answer will become no. And why is that? It's because when we fill this, we are filling with the congruence class of 0, right? So for GCD equals 3, 0 remainder will be 0, 3, 6, 9, 12 will become 0 again. So these are the possible values for any position which has 0. Similarly, for 1, all the possible values are 1, 4, 7, 10, right? And here the possible values are 3, 6, 9. Okay, so this is the same Okay, yeah, it can't be 3, sorry. It can be 2s. Very sorry about that. They can't be 3s over here, right? They can't be 3s because we're taking mod 3 itself. So, right, the possible values will be 2, 2 plus 3, 5, 5 plus 3, 8, 8 plus 3, 11, right? So these are the possible values which can be at the first position. So what we'll do is we'll put the smallest of each, right? We'll put the smallest of each. We'll make it equal to 0, 1, and 2. Now here we cannot put the smallest of each. We'll put the second smallest of each. So at this point, we'll put 0. Sorry, no. We'll put 3, and we'll put 4, right? Then again, we'll put the third smallest of each. We'll put 6 here, and we'll put 7 here. Then here we'll put the next smallest, which is 9, right? 9, 10, 11, 11. And then when we reach this breakpoint, we have nothing else left. Since we already used up 9, we can't put 8 over here, right? So there is no way to make it sorted. No way to make it sorted. We can't use the operation A of I plus K mod M to make it sorted if they have a GCD greater than 1 and the number of breakpoints is less than M by G. Okay. And they have a number of breakpoints greater than M by G. Right. In that case, the answer is no. If they have less than M by G breakpoints, then the answer is yes. Okay. Breakpoints or sorted blocks if you want to think in sorted blocks. Right. So now that we have done this much, we basically need to track for every possible value, of GCD G, right? We will keep a track of all the breakpoints. Track the number of breakpoints. Okay. So then if we ever come across a point where they're not co-prime, right? If they were co-prime, the answer is yes. If M and K are not co-prime, their GCD is G, we can simply output the number of breakpoints, right? Like we can simply check the number of breakpoints. If it is less than M by G, yes, otherwise no. Okay, so we'll keep a track of this across all queries. Okay, across all queries, we'll have a track of this. Okay, and how will we have a track of this? First observation is the GCD G has to be a factor, right? It's a factor of M. And that's the idea over here. We only care about the factors of M, right? M is already given the start, and the only important values are factors of M. Right, so GCD G is a factor of M. Max number of factors, so I think you should know this, but max number of factors of a number is roughly bounded by less than equal to cube root of that number, okay? So the max number of factors of a number is less than equal to cube root of that number, okay? So basically, cube root of M GCD possible, like cube root of M factors can be there. So that's the number of possible GCDs we have, okay? And if you see the question, M is given as 5 times 10 to the 5. So cube root of that possible GCDs we have. Sorry about that if this is complicated, but yeah, this may be a bit over your heads if you're not like seen these kinds of problems before. But so 5 times 10 to the 5 was the value of M, right? And if we take cube root of that, it's roughly 80. So for 80 numbers, we need to maintain the number of breakpoints, right? So keep track of number of breakpoints for all the possible GCD values. At most 80 possible GCD values will be there, right? GCD values can be there. This is equal to the number of factors of n. Okay, So this is one thing you should keep in mind, right? Now, how will we keep track of breakpoints? So this is the final part of the question, right? All this we understood. We know how to answer the queries. We know how to answer the queries. If it's coprime, just to say yes. If it's not coprime, find GCD. Check number of breakpoints. If it's valid, yes. Otherwise, no. Okay. Now the final thing, remaining thing about this question is how to handle updates. Okay, how to handle updates. Like if you remember the operation, the first operation is take some element I, assign I, a of I equals X. Okay. How do we handle this? Okay. And the thing is, the numbers are changing. So the number of breakpoints might change, right? So what we'll do is, um, for our array A, okay, for each factor of M, let the factor be F. So we'll call it F. Call it F. We will have a separate array, okay? So for the F factor, we'll have an array like 2D array. So for their total maximum 80 factors, right? We showed that there are maximum 80 factors. So it'll be N. So we'll have a 80 times N array, okay? For each factor, we'll have N values. And what will it contain? So will be A of I mod the factor, okay? So F factor, you could say. So for example, what are the factors of 6? For N equals 6, the factors are 1. So 1 we don't care of actually. Main factors are 2 and 3, right? These are the factors we care about. And 6, of course. So 2, 3, and 6, right? So for these factors, we will have 3 separate arrays, okay? The first array will simply be mod 2, right? So the original array mod 2, 4, 5, 2, 2, 4, 1, 0. So mod 2, we already saw what that was. That was 0, 1, 0, 0, 0, 1, 0. So this will be for factor 2 and the array, okay? For factor 2, the array is this. For factor 3, the array will be mod 3. So 4 mod 3 is 1, 5 mod 3 is 2, 2 mod 3 is 0. Sorry, no, 2 mod 3 is 2 again. Again, 2 mod 3 is 2, 4 mod 3 is 1, 1 mod 3 is 1, and 0 mod 3 is 0. Okay. And then similarly, we'll have factor 6. So for factor 6, it will be the original array itself, right? It will directly be the original array itself. 4, 5, 2, 2, 4, 1, 0, right? And these are the different possible values of GCD we can get, right? Now, we also keep a track of breakpoints in each, right? For each possible value of GCD or factor, we have number of breakpoints. So that's a different array, breakpoint array. We'll keep track of the breakpoints in each. So here, if you see, there is 4, 5 is a sorted block. This is a breakpoint. This is a sorted block. Then this is one breakpoint, one breakpoint, one breakpoint. Number of breakpoints is 3 here. And number of breakpoints is 2 here. And here the number of breakpoints is 2, right? So each time we get some GCD value G, we can simply check this array, right? And we can check the number of breakpoints. If it's less than M by G, we can say yes, otherwise we can say no, right? How do we do updates here? Let's say we change this value from 2 to 5, right? We change this value from 2 to 5. That's what happened in the second query, right? We changed the fourth value to a 5. So this value became from 2 to 5, right? So basically, if there were any breakpoints over here, we can subtract that from the breakpoint count. Then we can make this into a 5. And now that if there is a new breakpoint, you can see there's a new breakpoint here, right? So we can increase that from the breakpoint count and make it that 4. So we can do the update in big O of 1, right? In this array, we make the big O of 1 update for the number of breakpoints, right? Similarly here, what is 5 mod 3? 5 mod 3 is 5 mod 3 is 2 itself. So nothing changes. Number of breakpoint remains same. And what about here? 5 mod 2 is 1. So we can see that, sorry. This position got changed, right? Fourth position. So 5 mod 2 is 1. So we can say that this position became a 1 now. And now because of this, we can check, okay, there's a new breakpoint here. New breakpoint. Number of breakpoints became 3. So for each factor, we need to update it. We need to update the breakpoints. We need to update the array and update the breakpoints. So updates can be done in big O of number of factors. Okay. So big O of cube root of m, which is the big O of number of factors of m, which is roughly cube root of m. Okay. So updates can be done in this much. Queries. In queries, we are simply checking if it's coprime or not. And we're checking if it's less than m by g or not. So query is roughly big O of 1. The time to take GCD is there. The time to take GCD is there. But I'm considering that time as negligible. So I'm going to take big O of 1 itself. But actually, it would be log of m, I guess, right? I forgot time complexity of GCD is like log of something. Time complexity for GCD. Right? Yeah, it's log of min AB. So in the worst case, it is log of m, right? So each query, because it computes the GCD, each query works in log of m, right? And what is the pre-processing? We are making this array, right? Pre-processing. So first we have to find factors of m. So that's cube root, that's square root of m, right? Normal factor algorithm is square root of m. Then for each factor, we are making this array. So this will be n times cube root of m. Okay. So with this this much pre-processing, this much query, this much updates, we can solve this problem. How do we do updates? Well, we have this pre-processed arrays for each value of factor. It has the number of breakpoints. It has this array. We update the corresponding value and we update the corresponding value of breakpoints. So each update can be done in time of number of factors, which is cube root of m. What about queries? Each query, if it's just coprime, we can print yes. If it's not coprime, then we can check the number of breakpoints. If the number of breakpoints is less than m by g, yes. Otherwise, no. Okay. So this is the full logic for this question. And let's write the overall time complexity. It's going to become a bit interesting. Interesting time complexities we're getting to see. Overall time complexity should be so as m does not sum over all test cases, right? As sum over all m over all test cases is not true. So that's why for reprocessing of m's factors, t should be multiplied, right? So it will be t square root of m plus. Now that the factors have been found, the rest of it is straightforward, right? Because n sums over the number of test cases. So that's why n we do not need to multiply t, right? Sum of n over all test cases is fixed. So n cube root of m. So this is the rest of the pre-processing plus. Now let's say both updates and queries are happening. So it will be plus for each query. We can have cube root of m plus log of m. So this is the final time complexity for this problem. What about the memory complexity? Other than the n values, for each factor, we're storing a value. So we can say that the memory complexity is big O of cube root of m times n, right? To store this array. This is the largest array which we have, and there's nothing else being this value of f. So for each factor, stores I, and m goes up to 80, so it fits in the given memory constraint. So this is the overall time complexity and it's the overall memory complexity for the solution, right? So it's a slightly harder rated problem, 1800, 2000, something like that, right? Maybe it's even higher, I'm not sure. But yeah. If you did not understand, definitely, if you feel like you could solve this, but you're not able to understand, definitely rewatch this whole segment. We'll quickly go through the code for this. So the code is decent. So first we take NMQ as input. I define a vector FF, which is my factors. Okay, this is my factors of M. Then for each up to I up to square root of M, I'm pushing back all the factors, right? I is a factor and M by I is a factor if I divides M. So I find all the factors of M. Now I take in my input vector V, right? This is the input vector. Then this is the number of breakpoints. So I call this in INV. I think I meant inversions over here. It's not exactly inversions of array. It's the number of breakpoints of the array, right? But I've called it inversion vector. So let's call it inversion vector. It counts the number of breakpoints. Okay. Now this is the value vector, right? So for each factor, it stores the elements of the array, but simply take in mod of that factor, right? So factor 2, the elements of the array will be stored mod 2. Factor 3, they'll be stored mod 3. Similarly, factor 6, they'll be stored mod 6, right? So for each j in the factors, f count is the number of factors. For each I up to n, vals of j of I is equal to v of I mod of factor j, right? And then if there is an inversion, or if there's a breakpoint, I increase the number of breakpoints. Okay, so this is the code for that. Then now we are ready to answer the queries. The pre-processing is done, right? The pre-processing is done. For a type 1 query, we simply need to update the array. So we take in the value of I and x, I minus minus because it's one indexed. Then for each factor, there are total 80 factors at most, cube root of m factors at most. We will first, for the old value, we'll remove the number of breakpoints, right? If we'll remove the old breakpoints, we'll change the value. Now, if there are new breakpoints, we'll add them back, right? So we're simply removing the effect of the old element, changing the element, and adding back the breakpoints of the new value, right? So this is just making sure that the count of the breakpoints remains proper. Now for type 2 query where we need to answer, we are given our value of k. We find the GCD of m and k. If the GCD is 1, we can output yes because we know that they're co-prime, so the answer will be yes. We can just answer 1 and continue. Otherwise, we set a flag over here. So this loop is just to find which factor is which because I did not sort my factors, right? My factors just randomly stored in FF. So I'm just trying to find the factor equal to the GCD. Okay, I'm trying to find the factor equal to the GCD. Now, once I found that, if the number of breakpoints is less than m by g, right? So this is the condition we had over here. If we have this condition, then only we can make the array sorted using the operation, right? If the number of breakpoints is less than m gen z, because then I can put appropriate values in the sorted array and then make the values sorted, right? So if it is there, then the answer is true. So now if the flag is set, yes, otherwise no. So that's how we handle this slightly harder problem. And as you can see, the time complexity fits in, right? It goes up to 10 to the power 5. And like the dominant term over here, the main dominant term is like this n cube root of m, q cube root of m, which is roughly like 80 times 10 to the power 5 roughly. So that passes. Right? These are the dominant terms of our time complexity. Okay, so that's about it for G. If you had trouble understanding it, I think you should rewatch. Right? Yeah, the time complexity looks pretty cool. All below D were ad hoc. To be honest, B was not ad hoc, I say. B was pretty logical. What was E? I guess you can go rewatch it now. Yeah, E was an MX related problem. Yeah, it's a pretty cool problem, I would say. Yep, I guess it's late now, so we won't have like that, we have that question answer session thing, doubt thing. But it's already 2 hours, 50 minutes this video has gone on, so yeah. Good night, guys, especially the ones who stuck around even till the last question. Good night. Hope you learned something. Do rewatch the video if you got stuck. Do upsolve the questions which you could not do. And definitely check out TLE Eliminators self-paced course, right? If you haven't already. Hope you learned something and see you next time. Bye bye.